not getting the exact time to failure. And when R plus ith failure occurs, R plus I number of surviving units are randomly withdrawn from the test for all I equal to 1 to 3 x minus, not getting the exact hence we will have x r plus 1 comma x r plus 2 comma x m, that is the failure time points or failure times with a general progressive type to censored of state plus I number of which is nothing but the failure times of completely observed units, and r plus 1 r plus 2 extra rm be the censoring scheme. Due to some errors. Second reason is power or instrument failures or unmonitored intervals in long experiments. During the night, we may not be able to observe due to some errors. Like that, second reason is power or instrumentation failure. We will have several situations or unmonitored intervals in long. So a new model is required, actually designed for experience where failure during an interval are not recorded. The new censoring scheme that integrates both the generalized progressive type 2 and the general progressive type 2 censoring methods and is named as type 2 general type 2 progressive censoring method. We have already proposed one type 2 type 1 censoring method where failure during an interval are general. So in this slide, we have generalized new censoring scheme that integrates both the generalized earlier scheme and the general progressive type work here we present. Here we consider the experiment that start with n identical units and end with m failures are observed. Okay, where m less than or equal to n. At the first stage, from first to rth failure, as usual, Ri removals occur at each failure, where I equal to 1 to 3 extra R, and R is prefixed number. I will show the picture. This is the picture. At the first failure, we will remove R1. At the second failure, we will remove R2, etc. At the rth failure, we will remove RR number of units from the test. And after that, after the removals, and we will have some failures, but the exact time will not be. That is the data available. That is the data available. At the third stage, prefixed number. Okay. I will show. So we can picture group all these data: first stage data, second stage data, and third stage data, and prepare a likelihood function. This is the picture. Join at the first failure, we will remove R1. Then only we can estimate failure, we will remove R2 non-parameter. The rth failure, we will remove. So this is the joint RR number of joint unity or likelihood function. And after that, constant given like this. So that is a model. I think we will have some failures, but the exact and that is the data now in order to estimate, and the problem is so we can estimation testing and inference. We concentrate only on estimation problem. So for that we consider two distribution. One is exponential distribution, that is a random, and two distribution. One is exponential distribution, that is a random, and a failure rate likelihood or constant failure rate model. So there are plenty of applications are there with exponential distribution. So we consider exponential distribution. We computed the joint density like this. The maximal likelihood function is given like this, and it is not easy to because of the censoring components are there. We cannot evaluate normally. We cannot evaluate in the traditional using the traditional procedure. So here a lot of complication is there to estimate the parameters. So we have used Newton-Raphson numerical method to estimate, and also we consider Bayesian estimate by incorporating a gamma pair with the parameters alpha and beta. So the joint likelihood function also we can see like this, as we seen in equation 5. If we use the square error loss function, then Bayesian estimator shall be prior posterior mean, that is the equation given. And we have used the Metropol's Hansen algorithm to estimate using method. So that is a usual procedure. And we also simulated the data to examine the appropriateness of the distribution using this RS value 5 and 3. Theta is initial value is taken as 0.5. So these are the data analysis report. So MSE is found to be very close to 0. So we can trust in this model with exponential distribution. That is the common knowledge. And also we have computed confidence interval, average length and confidence probability, confidence percentage for these different values. And we have considered by a simulation using so AL and CP values are examined, and bootstrap confidence is calculated. So number of units put on test. M is the number of observed failures. R is the first phase number. S is the second phase number. We constructed 95% conference with using exponential distribution. A data analysis is conducted to examine the effectiveness to illustrate the usage. So this is the example. AAC, BAC, MLE, log likelihood value, everything are calculated. This is the data and estimate value, KS value, CM value, ACBC explanation of using Bayesian method. This is another set of data, and again we have computed estimates KS, CVM, AAC, BAC values with the different schemes. So these are the data. Okay. So another the second distribution is Weibull distribution. The only difference between exponential and Weibull is it has one more parameter, but constant failure rate model. So most of the failure data is either increasing failure rate or decreasing failure rate. So we have to use this type of distribution. So from using this distribution, we have developed the likelihood function. Here the likelihood is very complicated. We will not get the estimates by differentiating. So that is complicated. So we have to use numerical method. So Newton-Raphson, using the R programming, we have estimated the values. Also, we have used Bayesian estimation by using some prior assumption to the parameters. That is the method. And these are the under square loss function, that is posterior mean. The theory is given. Using MH algorithm, we have computed a simulation study is computed appropriateness of the distribution and parameter values, and it is found. We can see that the MSC values are going to 0. So the model is good. Confidence interval and is computed. Exact confidence and bootstrap confidence interval using MLE method. And using a Bayesian method, we have conducted the simulation, and MSE is going to 0. Here also we have computed bootstrap confidence interval, and 95% confidence also constructed. So a data analysis is conducted to to these are the estimates and their AAC, BAC, CVM, KS values, and the Bayesian, based on the Bayesian results, we have computed these parameters and confidence intervals. The suitability of the model was thoroughly examined using both the classical and Bayesian approaches. Goodness of fit assessments confirmed that viable distribution provides an aggregate fit to the data. Under the maximal likelihood estimation framework, the parameter estimates were stable and the model satisfied all required statistical conditions. Bayesian analysis yielded a well-behaved positive distribution with credible intervals that are consistent with the classical estimates. However, from the analysis results, we can conclude that the applicability of the viable distribution under considered censoring scheme for modeling these sets of mortality data in France. So, summary. This is the short summary of the presentation. Here we have proposed a new censoring scheme that addresses missing failure information. The statistical inference of exponential and viable distributions will be discussed with the help of method of maximal likelihood and Bayesian estimation, validated with the model performance through simulations, computed asymptotic confidence intervals, bootstrap confidence interval for MLEs and Bayesian estimates, respectively. Real data sets are used to illustrate the proposed censoring modes. These are some of the references we have used to prepare this paper. This is already submitted for the publication. It is under review. Okay, thank you.
Any question, please, from? Okay, I have a few questions. If no questions from the audience, I have one or two questions. This new model this new model is developed to incorporate the unobserved failure times.
Yes.
Isn't it? So my first question is this unobserved failure time, whether you have considered this as missing at random or non-random, informative missing. What is the assumption you have chosen?
Actually, that happened. The unobserved failures happens in an interval. Okay. So we have to consider that in the likelihood function that is unknown to us. The time point is unknown to us. Actually, we know only that happens in the interval.
Okay. That missingness, whether it is so you may assume it as random.
Yes.
Isn't it?
Yes.
Okay. Then you have used simulated data.
Yes.
So this what proportion this unobserved variation?
In the simulation that
in fact in the real world, in our cancer survival analysis, we come across more than 50% this kind of unobserved failure time.
Okay.
So and that is also that's why I ask you this question. So proportion of when that proportion increases, what is the reliability of the method, the newly developed method?
Okay, that we have to check, madam, because we have not think about the percentage of that unobserved data. We have considered situation only.
Correct. Okay, unobserved proportion. So if that is increased, the pattern itself will be changed.
Definitely.
Failure time distribution will be different.
Yes.
And the second thing is that if the failure time distribution, if that is informative, again this model development also the assumption can be made in this newly
Okay.
developed model. The assumption can be made only strictly at random, missing completely
Okay.
at random.
Okay.
The, isn't it?
Yes. 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 That's possible. That's possible.
So you can think of if in case if missing no is informative missing. So
Yes.
in
Yes.
such a situation, what kind of new this you can think of developing new models when the missingness is
Yes.
not completely at random, and the proportion when the missing proportion increases, because we come across that we use some imputation techniques and all. I have made a presentation in yesterday in the department that this is when we come across the missing proportion large,
Oh.
so we did imputation techniques, so
Oh.
using this real data.
Okay. 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 Definitely, I will be looking into that.
Okay. Okay,
Very good.
thank you. That very good presentation.
Okay.
Okay.
Okay. Thank you very much. Thank you.
Okay.
Thank you. Sir, thank you. Thank you.
Shall we go to the next presentation? Sadish sir.
Now there is few minutes, 4 minutes, because 6 is next time for the next presenter.
Okay.
For 3 minutes, now 5:57. By the time he will join, otherwise we can contact him and move to the next other speaker. I think he has not joined. Um, Earlier he informed that he is busy with some other engagements, but
Now,
hi,
I'm
okay,
free only.
okay,
Okay.
okay. Please,
Yeah.
Madam Fatima, you can introduce the second speaker and invite him.
Fatima will introduce Professor Anil C. Matthew, isn't it?
Yeah, it's my pleasure to introduce our second speaker, Dr. Anil C. Matthew, Professor, Department of Biostatistics at the PSG Institute of Medical Science and Research, Coimbatore, who specializes in biomedical data and epidemiology. Welcome, sir.
Audible?
Audible. You can share your screen and Madam.
PowerPoint, is it visible? Slideshow.
Not it. It is.
Slideshow.
I think it is there.
Is-
It has been. Yeah, you have to open the PowerPoint. Please. Otherwise, share it once again. Yeah, now it is coming.
Visible.
Yeah, it is visible, but okay. I think it is.
Visible, sir?
Yeah, it is visible. Yeah, now it is fine.
Okay. Good evening, respected Chairperson, Dr. Eliam Matthew, Conference Organizer, Dr. Sadish Kumar, sir, distinguished delegates, research scholars. It is a honor and privilege to be invited to speak at this international conference. Today, I will be speaking on addressing outliers in logistic regression analysis. So, why robust statistics matters in modern medical research? Electronic health records generate messy data. Community studies contain measurement errors. Outliers are unavoidable. AI and precision medicine require reliable information. And the presentation today was motivated by the work of Alessio, University of Oxford, on her paper, an overview of the robust methods in medical research published in Statistical Methods in Medical Research. Why statistics sometimes fail? Outliers exist, data are messy, assumptions are only approximate. Now, when you look for the outliers, vertical outliers, it includes a patient with average age, weight, and blood pressure suddenly has an extremely high cholesterol value.
Anil,
That means independent
your
variables.
slides are
Hello?
not moving. Slides
Not moving.
not moving. Now it's moving. Now type of outliers.
Yeah.
Oh.
Is it okay?
Okay, okay.
Now
Proceed,
moving.
please.
Okay. So a patient with average age, weight, and blood pressure suddenly has an extremely high cholesterol value. That is dependent variable, there will be variations. Similarly, high leveraging points, unusual characteristics compared with everyone else, but the outcome may still follow the expected pattern. A person with a high BMI, older age has a normal cholesterol value. Dependent variable may be normal, but independent variable will you can see outliers. And the last is influential observations. Just for a beginners, it is 10 friends, 9 decided to go to a movie, but the last boy convinced others and decided to go another movie. That means he is an influential person. So in medical data, one patient's data changes the estimated effect of a treatment from effective to not effective. That particular patient data is called influential observation. So what is robust statistics? Methods that are less affected by the outliers, methods that work even with problematic data. Why
Move the
biostats?
slides also. Please parallelly move the
Slides
slides
are,
also.
slides are not moving. 1 minute. Slides are not moving. Minimize silent കുഴപ്പമില്ല. Slides.
Slides are
Now
yeah,
moving.
now
Yeah,
moving
this
now.
is
You can make the make it full screen if possible.
full screen. It is not moving, sir. That is the issue.
Okay, 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 okay.
Now it's moving. Now,
Now we can see the type of outlays. That screen we can visible.
is it? Now,
No, no, not moving.
no. I think we'll keep like this way, sir.
Now it is what is robust statistics?
It's
Yeah,
okay.
that's okay.
It's okay now.
It's okay now. It's moving.
Yeah, it prevents misleading conclusions when outliers are in the data. Robust methods are more reliable estimates. Why are outliers difficult to detect in multivariable setting? A patient may appear normal in each variable separately, but become unusual when several variables are considered together. It is easy to detect outlier in the univariate data, but difficult to detect in multivariate data. For example, for a descriptive statistics like length of hospitalization, 1, 2, 3, 4, 20, everybody know that 20 is outlier. We already know that median is the most suitable average. But when we look at data set like this, it is a data of 204 patients, data diabetic patients, and the main study is aimed to find out obesity and its association with erectile dysfunction. By seeing nobody know which variable or which patient's case is the outlier. So the common problems with outliers are extreme or unusual observations can distort the results. In multivariate data setting, detecting outliers are extremely difficult. Why not simply remove the outliers? Outliers may represent the real patients. Deleting them may introduce bias. And robust methods reduce their influence without discarding the information. And the most important thing, it may affect the sample size and the power of the study also. So the key idea is don't wait, don't delete. Outliers are not to be removed. Their influence has to be reduced. One bad value should not change the conclusions. One extreme BP can inflate the mean value. So now let us look at the regression analysis. The relationship between outcome and the predictors and few extreme points can tilt the line. Gives less importance to extreme cases. Now, what we are going to do, the whole concept of robust statistics, when outliers are detected, it is more efficient to draw weight instead of to discard these observations. What we are actually going to do, the whole robust procedure is normal data we are giving full weight, and the outliers we are giving the small weight. Now let us look into the logistic regression. The outcome is dichotomous, that everybody knows it, and this is, for example, this is present or absent, and the independent variable can be anything, either continuous or categorical. Now, the objective of today's presentation is the are rarely used from the theoretical point of view. The aim of this presentation is the dissemination of the recent developments in the robust methods to encourage biostatisticians and clinicians for its applications in routine data analysis in clinical research. When should you use the robust statistics? Small to moderate sample size and field data, not lab controlled, community-based studies, and public health surveys. What changes it can occur? It can estimate more stable influence, inferences are more safer, odds ratios are still can be used. Now, when you look into the literature, the robust logistic regression, there are three ways. Currently, there are so many ways. Today's presentation, I wanted to highlight three methods. One is robust logistic regression, which anybody can do in the SPSS. Second thing is Bianco and Yohai. This Bianco and Anna Bianco and Vector J. Yohai from Argentina. They have suggested a method. And the last is Cantoni and Roncelli. They are from the University of Geneva, Switzerland. They suggested a method. These are the three things which I just like to address today's session. But in SPSS, when you look into it, there's no direct available there. So practical strategies, we have to detect the influential cases. So I just give you our own example, like the data for the illustration purpose, the study on the association between obesity and erectile dysfunction among type 2 diabetic mellitus patients data were taken. And the MI is 25.26. Obesity was 12.3% people are having it. And 31.9% people are having erectile dysfunction. And 27.5 of years. And sample size of this study were not 4. And if you wanted to detect the SPSS, let us see the logistic regression model, regression, binary logistic, and dependent variable, let us be erectile dysfunction, and independent variable is the obesity, adjusting the effect of age and alcohol intake. Now, when you look into the result, the obesity was, the odds ratio is around 2.725. The lower bound is 1.149, and the upper bound is 6.461, p-value is 0.023. But now let us see what is outlier. How many of them are conventionally, usually in my years, people will check the outliers of the study. I just illustrate how we can do the simplest way how we can do illustration. So same thing we have to do. Only we have to do the save command. When you put the save command, there are three options you have to click it. One is probabilities, that is hooks, and third is leverage values. So when you do this, the SPSS will display our these three additional columns. We can see it. And Cook's distance, a measure of how much a single observation influences the fitted model. Larger the Cook distance indicates an influential observation. But there are so many ways which we can look into it. A conventional way is 4 by sample size. Let us say sample size is 204. 4 by 204 is equal to 0.0196. The values more than 0.0196 are considered as the outliers. So outliers are coded with the number 0 and normals are coded with the number 1. So when you look into it, we can see the same thing. And when you do it, you will see so you have to transform the values. So this is the outliers which we can see. Cook's transformed 1 and 0. So when you see the total counts, 1 is considered as the normal and 0 is considered as the outlier. Total number of zeros will be 25. That means there are 25 outliers are in this data. The next step is we have to give weightage for it. All the outliers we are giving a weightage of and normal values which we are going to give a weightage of 1. We have to give weightage for it. So when you have to give weightage for it, you have to go for again transform option and compute the variable and weight which is equal to 1 as such it is in the current form, and weight is equal to 0.3 if the Cook's value, if it is more than 0.0196. So now you can see the weight part of it. 0.3 is for a the same logistic regression analysis. The only one difference which you can see, odds ratio has slightly changed to 5.119, and the lower boundary is 1.109. You can see an upper bound little higher level, 3.620. This is one of the conventional way which we can do the robust logistic regression model. Advanced methods are there, which is called Bianco and we have advanced methods like Bianco and your high robust logistic regression method. Instead of minimizing the ordinary logistic distance, Bianco and your high proposed a bounded loss function. See observed outcome. So in that, what we have to do is we have to install the residual part of it and bounded influence function and leverage weight. Basically, RI looks how far the observed outcome is far from the predicted model. That is pre-ascent residual. Psi RI is the reduces the influence of the large residuals, that is outliers. WXI reduces the influence of high leverage observations. And XI is the predictor or covariate information needed to estimate the regression coefficients. So the robust estimating equation in this model is formed by summing up overall observation, the product of the bounded influence function of the residual, the leverage weight, and the predictor vector. This weighted product is a set equal to 0 to estimate the regression coefficients. When you run the RStudio in the Mallows quasi-likelihood estimation instead of maximum likelihood estimation. For a beginners, I just explain you what is the difference between maximum likelihood estimation and Mallows quasi-likelihood by a small example, especially for the research scholar. For example, a person is performing nice music program in an auditorium. Some people are clapping for the music and some people are making sound for it. So the voice controller, what he can do is, he can give more voice for those who are clapping and less voice for those who are shouting for this program. So somebody use it, they looks like nice, but he's not. We are not asking somebody those who are shouting to get out from the hall. We are asking them to keep inside the hall, and only thing voice only we are controlling little bit. This is exactly what is happening in the Mallows quasi-likelihood estimation compared to the maximum likelihood estimation. So when you do this thing, the Cantonier-Roncesvalles method, the odds ratio again becomes 2.760. 95% confidence interval is 1.158 to 6.510. Seeing the results of this simple adjusted logistic regression, the odds ratio is 2.725. Robust logistic regression in the odds ratio it is 5.119. And Bianco and Yohai robust logistic regression, it is 2.746. And Cantoni Roncesvalles logistic regression, the odds ratio is 2.760. Now, when I look the area under the curve of all these models, adjusted logistic regression, the AUC is 0.575, and the robust logistic regression, AUC is 0.541, and Bianco Yohai robust logistic regression, AUC is 0. Robust methods may still offer advantages in estimation, stability, and resistance to contamination. Now look into the classic and robust logistic regression. Classic logistic regression, sensitive to outliers, whereas all the robust methods which I have suggested, resistant to outliers. In classic logistic, we can produce unstable odds. In classic logistic, we can produce unstable odds ratio, but robust logistic regression, it can produce stable odds ratio. And classic logistic regression, smaller bias under ideal assumptions, performs very well even under contamination. Which robust logistic regression method is preferred? The SPSS approach is a pragmatic approach and is not mathematical. What we can do, it gives weightage only, whether the value observed or far away from 0.01. Robust base command is for higher contamination, it is easier to reproduce it also. And so if you ask me, this is my own opinion only, I can assure that, but when you compare with robust logistic regression method, preferred. Software, SPSS way, SPSS needed. Bianco and Unina are software, robust based packages, and Cantoni Rogesty are robust based software. Bianco, your height is high, and Cantoni Rogesty is very high. Easy to use, SPSS is more easy to implement, others are little, those who are research scholars can do it. Recommend for the research, SPSS, I won't recommend it, but Bianco, your height, and Cantoni Rogesty, I will recommend if you're doing some good research papers. I'm going to conclude. Before concluding it, my take-home messages are: one, medical data are rarely perfect. Outliers, influential observations, and misclassifications are very common. Deleting outliers is often inappropriate. Outliers may represent genuine patients, and removing them can introduce bias. Robust methods reduce influence rather than remove observations. The principle is downweight and don't delete. Robust logistic regression provides more stable estimates and odds ratios. Cook's distance can be used in SPSS to identify influential observations and create weights. Cantoni and Rogetti methods are two major robust logistic regression approaches. Cantoni and Rogetti is currently more practical because it is implemented in R through the robust-based package. And robust methods should be considered routinely in community-based studies, public health surveys, and the observational research. And we have the developments for it for the t-test, survival test, and the ROC curve. And these are some of the references. Dr. Sajesh sir in the Thrissur has done a good work on this particular topic. And I hope you convinced how robust methods can improve validity of the clinical research findings. Any of the research scholars who wanted to continue in this topic, please contact me through my mobile number or email. My mobile number is 92452-87851. My email ID is anilpsdmet@gmail.com. And thank you.
Thank you, Professor Anil C. Matthew. Any question from the audience? Okay, very good presentation. So when we have outliers, many outliers, then we can use this robust logistic regression method model. So, and before that, in fact, this in medical research, we come across a lot of outliers. So outliers can occur while entering the data, that is data entry error or coding mistakes, instrument measurement error. So legitimate rare observations. So we need to look into such errors first before using this robust logistic regression model, because that type of outliers are not really outliers. So mistakes, data entry errors, so coding mistakes, these are, we need to, when we analyze a data, first step is to look into the data. So by doing taking this descriptive statistics, when we come across outliers, we need to check the data. Means quality of the data needs to be checked. Then if there are outliers, really they are outliers, this method is very good. So then you are saying that this in survival analysis also
It is developed.
robust
Methods are
you
started developing it. And we
okay.
wanted to be, our current area of interest is to go for these other models like survival analysis and some detection methods we wanted to do it. That is, this year we wanted to do some such studies. That's what I told. Any research scholars are interested, they can just contact me for that
Okay.
purpose.
Then when you did this sensitivity analysis, which method you observed the best?
Sensitivity analysis, no, it is
Okay,
not a
that can be
sensitivity
done.
analysis.
Sensitivity analysis can be done. We can fit the
Yeah.
model with all observations and excluding the these outliers. So then robust model fit. So that is another possibility to assess which method is better than this.
Yeah, we thought Yeah, we thought, madam, we thought about it, that particular thing. Yeah, we thought of including that also in this study.
Okay. Okay, good.
And like what Madam told is very important thing. Usually our medical field, since both of us are working in this for a quite long period of time, usually students, once they get the data, they started doing analysis. So the whole motivational talk is don't do it. First 1 week at least data cleaning, like what you have rightly pointed out. Spend the time for data cleaning, any errors, compilation errors, all those things. Then 1 week just exclusively for looking these outliers and all other things. Then slowly start doing the actual research work. This is my small recommendation only to the statistical research scholars who is in this audience, who is attending in this conference.
Okay, good. Yeah, thank you.
Thank you, madam. Thank you, madam. And yeah, thank you, madam.
So, should we go for the next presentation or any break?
Let us check whether the next speaker. There is a break because his time is 6:35 is after 6:35 is the time. So there is
Okay. So we have 5 minutes. We can have 5 minutes break.
yeah.
Okay.
In
So
between
we will join by 6:35. Is that
6:35.
okay?
Yeah. We can. The session is continuing.
Ah,
Those who can interact, no problem.
no,
And
I can be here at 6:35, or I should be here.
that's
I
left to
can.
you, madam. That's left to you. You can join left and join, or otherwise you can remain and do some other
No,
things.
I didn't get it. I didn't get you. We are going to the third speaker or presentation of the third
Third
speaker.
speaker. Yeah,
Ah,
third speaker.
okay. So we will finish it at the earliest.
Yeah, third speaker is Gopal, Gopal Vasak
Ah,
from ISI. Okay. Whether Gopal Vasak is away, not in the group. So
not.
anyway, we have to start at 6:35 is better.
Okay. Okay. Then I will take a 5 minutes break.
Okay, madam. Hello, Professor. Filippo, Professor. Hi, Professor.
Hello, how are you?
Fine, Professor. Fine, fine.
Oh,
Very nice to meet you, Professor. I virtually.
see you again. How has your year been?
Uh, yeah, fine, Professor. And everything going well.
Yes, yes.
Yeah.
I am now in my third official day of retirement, and it's been a lot of fun.
Okay, okay. We are very much grateful to you, Professor, even in your presence here
Well,
to
thank you. It
motivate.
is glad to be part of this. Uh, I actually tried to log in yesterday, and I wasn't able to get through. I don't know what the problem was, but you were having a conference yesterday morning too, right?
Yeah, 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 Professor. No, okay, 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 okay. Uh, Maybe due to network issues. Okay.
Who knows? But it's
Yeah,
good to see you now.
yeah.
Who is the next
Okay.
speaker?
Next speaker, Gopal Basak from Indian
Oh,
ISI, Indian Statistical
okay.
Institute. Yeah, Professor.
Excellent.
Let us wait few minutes for because it is scheduled at 6:35. That's why we are waiting. The,
I understand.
okay, Professor.
Hmm.
Hello, can you hear me, please?
Yeah, Professor, can hear you. Yeah,
Okay. Shall
good
we
evening,
start?
Professor. Yeah, Professor Basak. Yeah, here.
Yeah,
Yeah,
sure. Namaste. Yeah.
namaste.
Professor Gopal Basak,
Yes.
Fatima?
uh,
Yeah,
Fatima,
Fatima?
Yeah. Now we have our third speaker, Professor Gopal Basak from the Statistical Institute, Kolkata, a renowned expert in stochastic process and mathematical finance. Welcome, sir.
Thank you very much for inviting me in this international talk and conference. I'm really grateful to Professor Satish Kumar and others organizers. Now, actually, in this talk, also my our student uh, Polumi Jana, who has worked on this problem, which I'm talking, this really ongoing project, and I think here she's very excited to have this result and all that. So, which I'm going to present to you, is very fresh. Now, also my colleague, who is also advisor for supervisor for Olumichana, he's also here, Professor Samarjit Das. So both of them are online, I suppose, at this moment. So let me put the slides on. Let's see. Can you just 1 second? Let me make it visible. Yeah. Okay, window. Right. Is this the right one? I have to close the other window. Just 1 second. Okay. Yeah. So let me just. Yeah. Is it visible now?
yes, sir. Yes.
Okay. Let me make it full screen and then I'll start. Is this full screen?
Yeah, it is fine. Full
Okay.
screen.
Right. So the talk we are going to present is basically very old problem, old methodology, OLS, ordinary squares, and so we are work is ongoing on this. I mean, there are a lot of people earlier as well worked. So we are actually working on rethinking OLS efficiency limitations under asymmetry. So so let's see. So our outline is basically what's the proposed estimator. Very short. It would not be long talk really. Proposed estimator, variance expression, so optimal variance expression, and large sample distributions and simulation study, and possible real life applications we will be showing also. So this is very outlines, and story basically starts with this. OLS estimator under Gauss-Mark setup is, known to be best within its class of linear unbiased estimators, right? Now, this is of course not a. It has been used quite long time, and because of simplicity, it has been very. I mean, attracted huge number of practitioners as well as scientists to work on these things. So this gives an opportunity searching. Now, what would is there any better estimator? That means it's a best in the class of linear unbiased. We know when it is normal, then it's best linear and best unbiased estimator. But when it is So as a normal because it's also the most appropriate, best possible estimator. But what if we don't have normal class in that general or in general, or if we have non-linearity of the estimator? So can we have a better estimator than OLS? Of course, possibly a lot of people worked on this. Our focus is on asymmetry, the shape of the distributions. So we need to develop a symmetry or asymmetry. That's what we are focusing on. So you will see that how we are using it in the first possible things. So Anderson's result in 1962 proved the existence of such nonlinear estimator without giving any particular form of the estimator. Now, Knott's 1992 develop a particular form of estimate asymptotic property. So that's the we would like to show what's the nonlinear estimator as well as real life data. Okay. So model setup is basically the good old setup, the regression model y equal to x beta plus epsilon. So epsilon here is the, random error with the expectation of epsilon to be 0, but it can be asymmetric. Okay, so variance is finite, and we can assume higher order moment also depends on basically the since epsilons are assumed to be IID about time being. I mean, we will probably will not talk about anything else at this moment in this talk. So what's the proposed estimator? You see, the proposed estimator is the OLS versus x prime y. There's the OLS part that we are all familiar with. But here is a nonlinear part. Okay, is a for every component here, beta I, because beta is a p-dimensional, as you see that here, and y prime hy. The y and x are n-dimensional. So y prime h1y, y prime h2y, y prime hpy. So if there are p components of beta, then there are p components of this quadratic form also we can do. This is the particular form we are using right now. Things can be probably generalized in other directions as well. So here we have taken this component, which as you see the constant part. This is just to address the unbiasedness, because if we add the quadratic part, then this part will give you the mean of this quadratic part under certain assumptions. And this is the assumption hix equal to 0 or x prime hi equal to 0. Both would be applicable. Here I think we wrote the one-sided. But so this part gives me that estimator of beta tilde LPQ, what you say linear plus quadratic estimator. This is unbiased because of this added part here, sigma times this. Okay. Now, just one second. Right. So now AI, let me say that for we are sort of looking at the component-wise, maximization or minimization problem. We will be probably later on, not in this talk. Later on, we'll be working on the joint program also. So here, since it is component-wise, we take the define the estimator of beta tilde. We define at the moment, as I said, component-wise. We write that as beta I which we don't know, of course. I mean, it comes from the previous slide. As you see that if I had taken the ai prime y, the ith row of x prime x inverse, it would be written as exactly ai prime y. Okay. By the way, sorry, there's a typo here. All capital Y's will be little y here. Okay. Just to remind you the sample, the y is actually here. Okay. And now, so this is the ith component of x prime x inverse y. So that is coming. So next slide is telling you that how the exact form of this. So it would be exact form. You can write it out if you express the y and use the condition that hi times x or x prime hi. Remember this condition, hix or x prime hi would be 0. Actually, x prime hi also would be written, should be written here. Okay, so that's the form we are saying, and this is the ith row of x prime x inverse ai. So we will see that in many times. I mean that ai is coming. So the expression for variance, this you need not probably remember at this point, but you please remember that it comes from the variance of the linear part. That means epsilon is here, as you see, and variance from the quadratic part, which is epsilon prime hi epsilon. That's the quadratic part, and then the covariance part would be coming up. So covariance part would be the third order term. As you see that the cube third moment will come up in this case because it is the linear and the quadratic. We are taking the covariance of them. Okay. So that third moment picture, third moment basically appearing in the quadratic. Covariance of the linear and the quadratic part. Okay. So that's what we are separating them. If we write the variance, this is the variance from the quadratic part, and then I think, see, okay, see the variance from the linear part. There's a completely in this form, and this is the other part is coming from. This is the variance from the covariance part. These two. The covariance is coming all together like this, together. Okay. Okay. Right. Okay. This is possibly coming also covariance from the within the quadratic part. There is some part would be coming up. That's these two A and B are kind of separated this way. And this is the linear and quadratic part separation here in the C. And this is the completely linear part variance. Okay, these are the 4 terms. And I will skip this. I'll skip this slide as well. And perhaps the conditions we will probably tell you. So we take x prime x inverse. This can be written as summation ai square or aj square. Maybe it can be written as the kind of summation aj square would be in terms of diagonal entry. Because as you see that aj square when you do, then it comes as a x prime x inverse, x prime x, and x prime x inverse. So it turns out to be it is a x prime x inverse, the diagonal of that. And when you compute the diagonal, normally it would be adjoint of A by determinant of A. Adjoint is of lower order than determinant. If the determinant of the nth order, then adjoint would be the n minus 1th order. So adjoint of A by determinant of A, the diagonal would be of that higher order of that, and is a one less order of adjoint is that way. So that's why this is automatically, usually, it's a reasonable assumption. Once we have that, then summation AJ actually turns out to be order 1, and that also under JJ is really order of 80. So additional assumption of we are exploring on that if we can avoid it. But this is the second line, and after that, if we add these two, then we probably get all these other assumptions. Adding conditions on the other square term. So as you have noted that variance has two square term, right? One is this, and there is this. And finally, from the linear term. So this is the covariance term. This plays a crucial role because this has, remember, the C is the M3, is the third central moment. Okay, and M4 is the fourth central moment. So please make a note of it. This third central moment is 0 for the normal or 0 for any symmetric case. So which does not exist. Here that will play important role. Okay. Now, right, so mainly we use the central limit theorem on these things. That means we take the idea of these, really consider these two terms together. I mean, this, because this is the unbiased part. Okay, this is the linear part and quadratic part. This is totally unbiased here. And we show that this has a central limit theorem. And we show that this part goes to 0 in probability. So these together, that means xn part and as a central limit theorem and zn part goes to 0 in probability, then we use Slutsky to get the central limit theorem for this one. So that's the overall idea of the proof here, which is not very unusual. And then we use the natural assumption of fourth moment because we need the variance of epsilon j square, right? That's why we need the fourth moment. So proof we would skip. We would probably, we'd probably have more discussion rather. And what we wanted to show is that, asymptotic normality. So result is that saying root n LPQI, I component wise, converges to, that means has the same root n limit, converges to normal 0 AJ square. Yes? Any questions?
No,
Okay. Normal, yeah.
continue, Professor.
Okay.
Someone,
Okay, sure.
no problem.
No
No
problem.
questions.
Yeah. So here, please note that this is the that's those terms. This is the D part, and this is the A part, I think, and this is the C part. The B part doesn't arise because B part goes away with the probability convergence to 0. So what we are showing here, please see. I'll go back a little bit again to show. So basically their shape asymmetry is very much there, and you can see that bias from the OLS is of the order of 10 to the power minus cube, little bit higher, 7.7. Here n is 100 and n is 200 we have done, but here LPQ bias little bit less, but the same order. So it's 2.6 and 3.6, whereas here 7.7 and 8.6. So bias at the same order, but the bit less than the OLS. And variance of OLS, of course, are also 4.9, and in this case, the variance also has gain, but of the same order, 6.15, whereas it's 9.9. We have actually improved on the little bit order also, 10 to the power minus 4. That means in the sense that whereas this is 22, here it is 8. So which is quite substantial gain here, 22 versus 8, one third, nearly one third. I mean, so here the variance case we have also gained, and the MSC also we have gained here, exponential and chi-square here. And other distribution we have done gamma, truncated normal, and mixture up to normal. In a mixture is the big class. So mixture of any distributions you can do, and lot of cases are asymmetry, and mixture more data, and we take the here. So here this is the shape histogram of the density curve of per capita total expenditure. As you see, this clear skewed distribution. So comparison of different symmetry tests per capita expenditure, Cabilo, and of course it is there. All three tests is showing strong asymmetry, and that's what everybody expects also. So OLS and our comparison of OLS here, variance, we get OLS 124 and standard error is 11.17, whereas LPQ variance is 98 is better. Standard error also quite low. And efficiency gain, relative efficiency is 1.27 almost, so it's much lower than variance of OLS in the real data also. So I think this is our talk. If there is any questions, thank you. Any questions?
Yeah. Any question from the audience?
Our student and my co-authors are also student supervisor is also, so they may both join also. Please go ahead.
I have a question.
Yeah, please.
You have this. You are when usually in a we deal in medical. I am so these you have taken. You have only 3 variables. So how do you assess that these 3 variables? It is linear plus quadratic. So this LPQ estimate. How do you assess? First of all, it is linear plus quadratic using this real-time data.
Yeah, I think
That is based on those estimators.
Professor Samarjit Das also is here. So basically, we are actually not doing 3 variable. Actually, we are doing P variable, as you have noted. P means P dimensional. That means we can actually take into account any dimension, any number of factors in some. So yeah, Professor Samarjit Das also also.
If I understand your question correctly, so the regression is linear regression with p number of variables, but estimate of the underlying parameter beta, it is non-linear.
Sorry, not audible. You are not audible. Please.
Translate. I will sort of repeat that. Please go ahead.
Okay. So if I understand our question correctly, so basically our underlying regression is linear regression with p number of variables, p is any number, but underlying estimator of the parameter, so this quantity term has nothing to do. Linear regression is not a quadratic regression. It is a linear regression. That's all from my part.
Yeah, I think what he said that basically the similar things are as mentioned, but in a different way also. Basically we are saying that is a linear regression model is fine. Estimated to be the regression models is same. Okay, because of error may have a different asymmetry and other problem, because a lot of times even cancer research and other things, whatever be the model you have, error model may have the asymmetry.
Okay, okay, got it, got it.
So that's why we are taking advantage of error model to be asymmetric. We are proposing a different model for beta, different estimator for beta, which actually improves
Okay,
it.
okay.
So for
Good afternoon again, and it should be good evening anyway. Yeah, I'm Shyamala from Department of Mathematical Sciences from University of Zululand, and this talk is an overview of the statistical and machine learning models for future extractions. Is basically the students and the youth completed the masters and the PhD, and also is some of my work that I'm going to give you an overview of the existing models and also the machine learning models and its application in different domains like chemical process monitoring, where we do the fault detection and diagnosis, and also in climatology, and where the rainfall trend analysis that was done. That was a PhD study. And then in cosmology, estimation of the Hubble constant, and then the metal alloys, classification of metal alloys in material sciences. That was a master's project also. So that's what I thought of giving you an overview, but I'm not going to go deeper into any case studies, but it's just an overview of the existing models that we used. And yeah. So when I talk about University of Zululand, that's this university is located in Durban. It's 150 kilometers from Durban. That is one of the cities in South Africa. And this is a previously it's a disadvantaged university, and we got like 6 universities in South Africa, and Zululand is one of them. And it's a comprehensive university. That means we can offer degrees and also diplomas. That's why it's called a comprehensive university. And it's located in Mbangeni. That is the main campus. And there is another campus that is the engineering campus. And also we offer diploma courses in Richards Bay. And that is the industrial area where it is. And then we also got like 4 faculties in university that are like Faculty of Education, where they focus more on teacher training, and then humanities and social sciences, they are language studies and all other things. And then we got law and commerce and political sciences, those kind of degrees they offer under the commerce administration and the law faculty. And I'm in the science, agriculture and engineering faculty. So it's the Department of Mathematical Sciences. We got 3 programs running, that is the pure mathematics courses, and also applied maths courses, and also statistics. All our degree programs are dual programs that we combine the degree with other departments. We've got 14 departments in agriculture and science, agriculture and engineering. And we also offer master's and PhD studies in statistics, applied maths and mathematics. And so we got like a very strong focus on teaching and learning, community outreach, and on research, because these are the 3 pillars that we normally academics they need to balance in our career as a faculty member in the department. So we always have the teaching and learning, community and outreach programs, and I mean, together with our research, what we are doing. And we got opportunities, especially in the faculties, like we have different area of department science, especially in physics, chemistry, and in mathematical sciences. We are focusing on different area like renewable energy and applied statistics, those kind of thing. I mean, even now these days in engineering also we got opportunity there, and water resources, also the health, biochemistry and microbiology, they do more research in the health sciences, and computer science, they do more in the technology side. And we also support bursaries for postgraduate students. There is a National Research Foundation. They get bursaries through them. And there are also other international fundings are available. And postdoctoral, there are also local NRF, National Research Foundation. They support the postdoctoral research. And also we got industry collaborations and other partnerships, with international partnership with MOU that we signed with some institutions from overseas. So this is an overview of Zululand, and yeah, I'm from there. So now in this study, I said is an overview for future extractions using statistical models and machine learning. So why need to have that kind of motivation here? That why need to have that to use the statistical or machine learning models? Because we know that this is a data-rich environment. Whatever we do, because of automation and all other things that is happening, and we got plenty of data available. So that raw data that we have sometimes are like messy. Messy means it's hidden patterns are also there, and also noise is there. So it's very difficult to understand that. So for that reason, and on the top, it's also very high in dimension. So we need to have some kind of a model that can extract those features, or they maybe cluster them based on the patterns that we are looking for. So it's very important. So feature extraction will make the data more compact and also more meaningful, and they represent the data very well. So especially statistical models, if we use the statistical models, we can look at the, identify the relationship, especially the principal compound analysis. Those classical models are very good to look at the correlation between the variables. And there are models, they can also look at the autocorrelation between the variables and also the patterns that we are looking for. That's why statistical models are widely used. And on the top, these days, machine learning models are also widely used because they can learn features from the data. We can use them to predict, and also we can use them to classify. So in other words, feature extraction is very important because if you use a proper model and a very good model, we get a better feature, and that better feature will also improve the performance of the operations or whatever we are looking for. I mean, from the point of process monitoring, and that, from that point of view, it's very important to have a very good model so that we can optimize the process operations. So here, I just wanted to say in general, the role of statistical and machine learning models are said. I mean, they can handle large and complex data set efficiently. Also discover the hidden patterns, that is, and also the relationship that between the variables that we are looking for, and it helps us to get a very good prediction, and that will lead to a good decision making process. And it also improves the classification, accuracy of the classification, and also whatever you are doing, like a regression or forecasting. And in process engineering, those kind of area, it supports automation, and also it helps to maintain the monitoring, in a good way. If you use the statistical or machine learning alone, or maybe a hybrid model together. Okay, so that's the role of the statistical models and machine learning. Okay, so what is feature extraction? Feature extraction means when we have a raw data, and they can transform data into informative features, and that can be used for analysis or any further modeling or whatever we are looking for. For example, we have a raw data, and then we can use the different models, hybrid models, and then we can come up with the information. So that's the basic definition of the feature extraction. I think you all know about it. So in this study, in the studies that we conducted so far with through the masters and PhDs. We used singular spectrum analysis, that is a spectral techniques, and that's data adaptive techniques. That is and we also used different variants of SSA because based on the data or based on the relationship is linear or non-linear. So we did some modification of the basic SSA. So it decomposed the series. It's any times, it decomposed the time series into different components. Those components are called trend components are there, oscillatory components are there, and noise components are there. For example, if you can look at this, this is the basic time series, and once we apply SSA, we will get different components. So that's we call it multi-level decomposition of the data. A nice thing about this thing is it's adapted to data. We don't need any basis function or anything, and it's also take care of the autocorrelation, between the points in the time series. And the other one that we used is the empirical mode decomposition. It also works. It also gives the multi-scale decomposition, but it's basically it's through a sifting process. That's what they decompose the signals into IMFS, so intrinsic mode functions, and through sifting process. And it's also very good for non-linear and non-stationary kind of data. And then the other one, the singular value I think we all know about singular value decomposition, but that is the core of principal component analysis, and that we use PCA widely for dimensional reduction and all other things. So that is SVD is a very basic thing. Even SSA, singular spectrum analysis, incorporates singular value decomposition. So I mean that is not something that like something unfamiliar. It's very, we all know about that. And the next one that we used wavelets. We used wavelets because when we want to compare actually singular spectrum analysis, empirical mode decomposition, and wavelets are the spectral techniques. And they also, wavelets decompose the signals into time frequency components. So if you have the, it will, but it will have like a reconstructed signal, but the multi-level reconstruction that we can do, it depends on the level of decomposition. And it's very good for, especially when the data is non-stationary, we can use it, and there are we've got good results with that. And it's also denoise the signal like SSA, and also EMD. It can decompose the signals, and the feature extraction is it can do a very good feature extraction as well. But there are advantages and disadvantages when we look at all these different methods. For example, wavelets, if you want to use wavelets, we need to have a mother wavelet that we need to decide. Like it should be, we used HAR and WG's wavelets for some reason, especially in the literature for process monitoring side. Most of the people, they use the HAR and WG's, but that's what we have to choose a wavelet. But SSA and EMD, the basis functions are adapted to data. So it was a bit straightforward. And also in wavelets, the length of the signal should be like a dyadic because it got some end effect limit and all other things. So the length of the signal we should be very careful the way that we choose. But for SSA and EMD, we can even apply very short noisy data. So these are the basic methodology, basic framework, basic method for all these things. So SSA, like you need to create a lag trajectory matrix from the time series you have. Then once you have the lag trajectory metric, means based on the autocorrelation function or the maximum decorrelation point, you embed the time series into different lags, like use an embedding dimension. So you come up with a lag trajectory matrix. It works similar like a dynamic PCA. Then you do the singular value decomposition. By doing singular value decomposition, you got your eigenvectors, eigenvalues, and all other things. Then after that, you can group them based on the eigenvalues, because if you took, and when based on your principal components and the eigenvectors. So group them based on like the first component together and the second components together and third components like that. So that's the way that you get different levels. Then you do the diagonal averaging because you need to come up with the, to get the multi-level decomposition, you do the diagonal averaging through the grouping. So we say normally this is a LAT embedding the first step, and then singular SVD, and then grouping, and then we have the reconstruction. So this is the framework for SSA. This is very basic SSA, and we use the covariance matrix to when we apply SVD. But when we did the variation, so variance of SSA, I use the multi-dimensional scaling. I use dissimilarity matrix. I use kernel dissimilarity matrix. Those kind of things that we used. That are the variants of SSA that we do. And for the wavelets, what is that? So original signal you have, then you have the wavelet decomposition, that is approximation signal and the detailed signal. Then you decide how many of them you need to retain, then you do the reconstruction. So the reconstruction is done like that. So when you have the first signal that is decomposed into the approximation, the first approximation signal and your detailed signal, but then you decompose the approximation signal into again your A2 and D2, and then you go, you proceed with that. So once you end with all the, the decomposition, you can reconstruct them by combining the last approximation signal plus the other details you have. So that's what we do the reconstruction in wavelet. And for EMD, empirical mode decomposition, I said it's a sifting process. That's what we extract the intrinsic mode functions, IMF. So that is the, you have to identify the upper envelope and lower envelope, then you take the mean, and then, you remove that, you have a residual signal, then you continue the same process again until you stop the sifting process. So that's what empirical mode decomposition did. But all these things are, the literature is available and is well explained that also. In EMD, there are extensions. There are a lot of extensions happen. This is a basic EMD process. So there are also extensions of EMDs available. So now in machine learning, these are some popular machine learning techniques, but there are other machine learning techniques there. I didn't include all of them here because it can capture the nonlinear relationship, especially the neural network and autoencoder, because when we were using the nonlinear version of singular spectrum analysis, I used the autoencoder because as I said, SSA got a singular value decomposition part, and that part was modified with the autoencoder. So that's what we came with the nonlinear version of SSA. So then these days, convolution neural networks, CNN is widely used, especially in the image processing and all other things, but we never used CNN. We use mostly in the neural network, artificial neural network, ANN and autoencoder, and one student used the two students, they use the support vector machines. And also together with this, we also used random forest, decision trees, gradient boost. Those kind of techniques are also being used for, to extract features and classify data from different domains. So in other words, machine learning approaches can capture nonlinear relationship, and it also is very useful when you have a very large and complex data set. And the only thing is you should be very careful when you do that, when you tune the parameter. Sometimes overfitting can happen. That's the only disadvantage, but it works well with when you have a very large data set. So that's what the machine learning approaches they can do. But as I said earlier, we mostly also used hybrid models because statistical methods can filter the time series or filter the data. Once you have a filtered version or a multi-scale version of the data, then we can apply machine learning techniques to extract the features. So that also we call it hybrid models that we use. So these are the case studies that we use these models. As I said, I took four case studies here. One in chemical process monitoring, where we did the fault detection and diagnosis in the chemical processes, and that's what I'm going to describe that. And the next, then I'll explain. These are the work, the projects that we completed. So we all know that for a reliable, safe operation of any process industry is very important, because we need to protect the human life and health, same time the environment, and also the output of the product, optimize the product that we are looking for, because we need to optimize the process. And that's why it's it's very important to have a very reliable fault detection and diagnosis method or framework to make sure the operations are very successful, and also because we need to detect the fault as early as possible, so that we can do the accurate diagnosis of the fault. So that's why these days fault detection and diagnosis has developed into a major area of research. It's intersecting control engineering, mathematics, machine learning, and statistics as well. So in the modern day process, any chemical processes that we have is very difficult to control and very difficult to manage, and also very difficult to diagnose the fault, because they are large in scale, very highly automated with a lot of sensors and everything available, and the process, the unit itself is very complicated, and also they have advanced control system. So because of that, data-driven techniques are very, very popular among other models. There are mathematical models, and also there are knowledge-based models. So although in those models, you need to have some kind of a previous knowledge about the process or the plan that you are, monitoring. But when it comes to data-driven, the data can talk, that data can give you useful information. So that's why data-driven techniques are very popular these days. Among data-driven techniques, multivariate techniques are very good, because they can handle the correlation between the variables and also autocorrelation. And among that, principal compound analysis and partial least squares are very, very popular, and they are the classical techniques that is used in the chemical process monitoring. But I used mostly principal compound analysis when I want to detect faults and in process engineering. So this is the basic framework of a process monitoring by using principal compound analysis. I will just explain the framework, then I'll explain that the other part. So here, when we apply principal compound analysis, and it can separate the data into two space. One is we call the spore space, where the principal compound, and then is the residual space. So in those spaces, we can use two different control charts that are the squared prediction error, and also the Portland T-square chart. And they know the control limits and everything are, we have to determine based on what the normal operating condition of the process, or the data that is taken from the normal operating conditions. We use simulated case studies. Also, we use the industrial case studies. So these are the control charts that we normally use for the fault detection. Once we detect the fault, then we can always diagnose the fault using the contribution plot. We have contribution plots for the spore space and also for the residual space. So the process monitoring using PCA, it's good for the large set of correlated data, because it decorrelates the data, and also useful for achieving stability and reducing variability in a multivariate process. But there are limitations, because it's a linear method, and we can only extract linear relationship among the variable. If the data is non-linear, it may give you a false information. It may not be useful. But there are variations of PCA already, we used. That is one for nonlinear relation, nonlinear data. We use the kernel PCA, and for the data with the dynamic and with the autocorrelation, we use the dynamic PCA. And also there are different nonlinear PCA also using the PCA with autoencoder. There is a version called nonlinear PCA is also there. So there are extensions of PCAs available for a nonlinear data, but this is just the basic framework. So as I said earlier, fault detection, we conducted the fault detection using the Hotelling T-square and the Q statistics. Q statistics, the squared prediction error chart, and the fault diagnosis are using the contribution plot. Now, when it comes to a process data, we will say that they are multi-scale in nature because all different events are happening at different times at a different frequency level. For example, if you have an original signal like this, there are other hidden things process are happening, because if you have a sensor failure, then you have a sudden change in the data. Or if you have equipment failure, so that also sometimes you have a sudden spike there, and maybe a wider side spike there. But any equipment degradation, that happens very slowly over the time. And also the oscillatory noise or random noise, they are also happening very slow, spread over the data. So if you can see that all different components are one single time series data or process data, you have all these different components, all these things are happening. So for this reason, you need to have a technique that can handle all these components separately. So that's why we used singular spectrum or empirical mode decomposition or multi-scale or wavelets to decompose the data into different levels, so that we can use those different levels based on the application that we are looking for to detect the faults or diagnose the faults. So this is the basic framework. With SSA we have the SSA or wavelet or even empirical mode decomposition. So we have the process data, then we use the spectral techniques or statistical models, then we decompose the data into different levels. Once we have those levels, we can use principal component analysis to monitor them. That helps us to detect the fault. We can use the contribution plots to diagnose the fault as well. So this is the basic framework of the process monitoring, to represent the data into, we call it multi-scale process monitoring framework by using all the spectral techniques and PCA. So other case study, so as I said, in all these case studies, we use the simulated data, simulated case scenarios, and also the benchmark data, also real monitoring, real plan data. So we managed to detect the faults. Each and, as I said, each and every method has got its own advantage and its own disadvantage. It also depends on the data that we have. With the data with the highly correlated and very dynamic, SSA performed very well. But if your data is very non-linear, and SSA couldn't do it very, very well, because SSA is a linear method, but the variations of SSA managed to detect. But overall, empirical mode decomposition was the one that gave us a very good results. But wavelets, as I said, the challenges were the choice of the mother wavelet. So so as I said, it's not like one method is very good. Depends on your data and the application that you are looking for. So in cosmology, students, they use the machine learning techniques to estimate the Hubble constant, because these days the Hubble tension is there. Hubble tension means when you have the observational data, the parameter of the Hubble constant, it's different. The values are different. But when we train with the machine learning, and they are almost very close to very close to the value where cosmologists, cosmologists, they want it. So it's actually Hubble constant is the cosmic speedometer. It will help us to understand the expansion rate of the universe, and is very important for testing cosmological models. So that's why these days cosmologists are looking at Hubble tension, and they are also using machine learning models together with the dynamic model like the lambda CDM model and the extended version of the lambda CDM. They are mathematical models, but on the top they are using machine learning and statistical models like the student, the master's student, she used chi-square and also maximum likelihood estimate. They are the basic statistical model she used together with support vector machine, support vector regression she used, and she used the random forest and decision trees and gradient boost, those kind of things to estimate the Hubble parameter. But among all of them, random forest gave a very good results here. So why? Because it can handle complex astronomical data sets, and also it can learn nonlinear mapping between the data and the Hubble constant, and also it can give us an alternative method that we can use together with the mathematical models. So, I mean, the data sets collected from the Pantheon plus data, and then these are the different machine learning techniques that is used together with other techniques, and came up with the estimation of the Hubble constant. So one study in the material science, that is the metal alloy density classification. The student used the support vector machine to classify the metal alloys, the density of the metal alloys. So the student classify the metal alloys into group-based groups, into different groups based on their density, low, medium, and high. That's what the student they did, and that is, it was funded by Mintech, that is one of the research institute in South Africa, and that was the master's project. And the PhD student, he used empirical mode decomposition to identify the rainfall trend in South Africa, especially collected the data from the different weather stations, whether you used EMD and he came up with the different IMFs, and then he captured the hidden pattern across the, across different time scales. On the top, you also use some forecasting techniques, regression and things to analyze the impact of this rainfall in agriculture. So that was also done, and that study is already completed now. So that's what the student was doing. And he didn't use other method. He just used the EMD. He didn't compare with wavelets or anything else. And then I just wanted to say the advantages of these methods, statistical and machine learning. It can interpret the data very clearly, and it's very easy to explain and easy to justify your problem. And also the robustness is there. If you have when you have like a very short data, very short and noisy data, especially SSA can perform very well, but not wavelets. And so there are also, if you look at the spectral technique, statistical models, it's well-established method with proven, proper statistical properties are explained, no assumptions are there. And also the computational cost is less compared to the machine learning. Machine learning, especially when you use the machine learning models, the computation is very high, but statistical models, it's very low. And flexibility is there. And when you have a very good data, very large data, okay, definitely machine learning models are very powerful. And you can, automate the feature learning process, especially in the process monitoring side. We need the automation. So in that way, automatic feature extraction and can be, you can do that. Especially you can identify the hidden patterns, like by decompose the data into different level, that is automatic feature extraction is happening there, and especially using the spectral techniques. So that's very, very important in process engineering side. And when you apply all these techniques, also there is room for the continuous improvement. When you have
Excuse me. Finish it in 2 minutes. You have 2 minutes time.
Okay. So it's the last slide that I'm going.
Oh,
Yeah.
oh,
So
okay.
the limitations and the about advantages I talk about that, and the limitations are like sometimes the assumptions are there. PCA, you have to assume that data is stationary and or linear, and and also you need to make the data very you need to the missing data, missing information. You need to fill those things, and limited scalability is there. But for machine learning, we all know that overfitting is there if you don't do the parameter tuning up the parameter properly, and also the high computation is, and also it need more data when we want to apply machine learning techniques. So in summary, I will say that statistical plus machine learning methods are complementary to each other. And because it can work well with the small data set and especially the statistical models, and machine learning can handle complex, nonlinear, and big data. And if you combine them, and it's very good because we can get a better explanation and better feature extraction. And it helps for decision making in complex system. And it also maintain the the process operations, and it helps in if anything, if you want to detect the fault as early as possible, that these kind of models is very powerful, so it can prevent accidents and all other things. Okay, thank you.
Okay, thank you.
That's it.
Any question from the participants? Any question? I have a question that
Okay.
is, we know that this feature extraction is commonly used in many field statistical methods like principal component analysis, factor analysis. When we fail this linearity assumption, we can go for this several machine learning techniques. My question is, what is the criteria of choosing this machine learning technique? There are several machine learning techniques, no? So neural network, support vector machine, the random forest, decision tree, and so on. Several techniques are there. So which technique can be used for our data? So
Okay.
what is the criteria of choosing appropriate technique?
Okay, I mean, for in process monitoring kind of a domain, when you have a data with complex and lot of variables, so there is no particular, especially with combining with the spectral techniques, widely used nonlinear PCA with the autoencoder or ANN or support vector machine. That's what people they used, and random forums also to some extent they used. I mean, that's what that is happening in the literature. But when it comes to estimation of Hubble constant, those kind of domain is a support vector regression they used, but recently random forest outperformed well compared to the decision trees, because random forest are the extension of decision trees. So you need to carefully look at which way you can. But most of the studies these days, random forest outperform all other existing machine learning techniques in that domain. For the material science kind of a domain, when we do a classification and support vector machines, people they used, but there are I don't know much about other techniques that they are available, but they performed very well. So in general, I have to say that there is no particular criteria which method works, which machine learning works, which machine learning not work. But especially you need to look at your data. If you have a very, very huge data and you are doing something like images or something like that, deep learning and RNN, those kind of CNN, those kind of techniques can be used. But if the data set is not too big, or it's okay, very, very, very small, and these are, I mean, as I said, the one that I mentioned we can also do. But it's always nice to apply maybe a couple of techniques and see which one gives you a better extraction or better performance. Then you can take it from there.
These methods we obtain this the best we are dealing with, suppose we are dealing with several variables. So then these feature extraction using these machine learning techniques, we will be able to identify which variable will be the highest importance. So
Okay.
likewise,
Mm.
in regression model, we get high predictor variables, and we can identify which predictor variable will be the most important. Likewise, here in the feature extraction, feature selection, do we get the importance of each variables one by one?
Yeah, I know the student who was he was doing the material science study. He had over 50 variables available when he was doing the density estimation. So in that case, he just apply the basic PCA first, and you look at the correlation metric, and based on that, he selected the important variables. Then he managed to apply the support vector regression. I understand that when you have a large number of variables, the computation and all other things are very, very challenging, especially we just use the machine learning. So our basic PCA, the classical PCA, is the best one to reduce the dimension first and select the important variables. Then you apply the machine learning techniques. So that's what we were doing in most of our studies.
Okay, thank you very much.
Thank you.
We will move to the next presenter, Fatima.
We have our fifth speaker is Professor Vivekananda Roy from WSTA University, USA, a leading expert in Markov chain Monte Carlo methods and Bayesian computation. Welcome, sir.
Thank you, Fatima. Can you hear me?
Yes.
Okay. So I'll try to share the slides. Let's see. Okay. Can you see my screen? Hello, Professor.
Yeah, we can hear. We can see the screen. It's a fine perspective.
Okay. Thank you so much. Yeah, thank you, Professor Kumar, for inviting me to give a talk here today. And so there is an advantage being the last speaker of the session, because I'm going to use the materials that my previous two speakers already have covered. And in particular, the question that was the last question that was asked about feature selection. Hopefully, by the end of my talk, I'll give a tool that you can use as you go back to your office or tonight or tomorrow morning, and you can use this tool to extract to select those features, the important features. Okay. So without further delay, so I'm going to talk about MCMC algorithm for variable selection or feature selection, high dimensional feature selection in linear regression. And I'm thankful to Professor Bossert for nicely introducing the linear regression and the OLS. So I'll use those materials as we move. Okay, so Markov chain Monte Carlo algorithm is a widely used method for sampling from intractable distributions in statistics, machine learning, physics, chemistry. Among the methods, the MCMC methods, the Markov chain Monte Carlo methods that are available, Metropolis Hastings by far the most dominant one. So I'll briefly talk about that and some of its variants before I move to introduce this new approach for constructing efficient MCMC algorithms. And especially I'll use the Bayesian feature selection example. Okay, and I'll end with a very high dimensional example from client science. So, what is an MCMC algorithm? MCMC algorithm, basically what it does, it runs a Markov chain with the target pi. So pi is my target density. It's a PDF or a PMF. It is defined on some space X, which can be, for example, the d-dimensional Euclidean space. So I want to sample from pi, and I'm assuming throughout my talk, and I'll give some examples, I'm assuming that I'm handling densities which are either high dimensional or so complex that IID sampling is not feasible, which is extremely common these days. So what does a metropolis systems algorithm do? It runs a Markov chain, as I said. As a Markov chain, is a simple stochastic process. It has a simple dependent structure in the sense that given the present and the past, future only depends on the present. So basically, I need to know how to make one-step transition, and then I can just repeat that. Okay. So I'll just tell you how the image algorithm or metropolis systems algorithm make one-step move. So suppose xn, so n is the iteration number, xn is the current value of the Markov chain, and all I'll tell you how to move to xn plus 1. What it does, it draws a candidate point, which I'm denoting by y, from some density q, okay, and then it decides whether to accept that y as my next move or not, as my next step or not, based on some acceptance probability, which the formula I have mentioned here. Okay. Now, as I mentioned, so it turns out that under very mild conditions on this proposal Q, this results in a stationary Markov chain with this target pi as the stationary density. Okay. So, I have not mentioned these mild conditions, but you can basically choose arbitrary Q. So that means by varying Q, you are getting different valid Markov chains, different valid MCMC algorithms. Some are very popular. One of them is the random walk metropolis algorithm. So let me explain it when your X, the state space is the d-dimensional Euclidean space. So in that case, Q is for random walk, Q is often chosen to be the normal density. Okay, so the d-dimensional normal density, which is centered at my X, the current value, with some Helms-Commons matrix, which is H times the d-dimensional identity matrix. H is what is known as the scale parameter or the step size. Okay, so basically, if I want to, another way of visualizing this is, so X is your current value, that xn, right, at iteration n, and you are just simply doing a small perturbation. So that is X plus I, where I is a draw from a normal density. That's it, mean zero normal density. Okay, that's it. So you are making a Euclidean perturbation to your current value to generate your candidate point y, and then you accept or reject depending on this formula before. So as you can see, this proposal density Q, this normal density here, doesn't use any information about my target pi. Okay, and what it turns out that, although it's very popular and extremely easy to use, but it suffers from slow mixing in high dimensional and, complicated situations. So that, motivated people to develop what is now called informative MCMC algorithm, where you're trying to use some information about the target density to construct your proposal. Okay, so for example, the MALA, the metropolis adjusted Langevin algorithm, which also uses a normal proposal density, and again, Helms-Commons matrix is H times identity, but the mean is not simply a X, but also governed by the gradient of the log target. Okay, so the hope is, as you are using the gradient information in the proposal, you are going to, move to the higher mass region very quickly and hopefully stay there. Okay. Another very popular MCMC algorithm these days, known as Hamiltonian Monte Carlo, also use gradient information and momentum and things like that. And I'm not going to explain all these algorithms, but these are simple to use, and there are packages, softwares that you can use to implement these algorithms. Now, so these are good. This uses gradient information, but still, it is making the moves in in the Euclidean space, in the sense that it does. So your target density, our target is a probability density function, which comes with certain properties. All these algorithms that I mentioned, this does not use the properties of a density function. In particular, what do I mean? So here are two stalwarts. On the left, we have Sierra Rao, who left us in 2023, and on the right, we have R.A. Fisher. So they thought about these, they thought about the natural geometry where the probability densities live, and what can be a natural metric in that space. In particular, in that 1945 paper, when Sierra Rao was merely 24 years old, in that paper, where he came up with, especially for the students in the audience, where he came up with, these groundbreaking ideas of the Kramer-Rao lower bound, the Rao-Blackwell theorem that we study in the undergrad textbook. He also introduced this information geometry in that same paper. It is a fundamental paper, and I request students to take a look at this paper. So they came up with this, what is known as now the Fisher-Rao metric. So here I is the information matrix. They showed that this is the natural metric in the space of probability densities. So you can pick up this as a Riemannian manifold, where this is the natural metric, so giving you the geodesic distance. And a few years back, Mark Girolami used this idea, the information geometry idea from Sierra Rao's paper, to come up with what is called the manifold versions of the Mala and the HMC algorithms. Okay, so let me just give you the proposal density of the Mala. Okay, the M Mala, the manifold Mala. Don't get bogged down in the formula, but you can see the proposal density. Okay, let's recall what was the proposal density of the Mala. The proposal density of the Mala was that it's a normal density with the variance covariance matrix being simply H times identity, and the mean be simply X plus H by 2 del log pi X, right? The gradient of the log target. Here, the mean and the variance is more complicated. In fact, they both, the mean and variance, not only depends on the gradient information, but also the higher order derivatives. The information matrix and its derivative, it depends on. So, yeah, you can see that it is complicated. The formula is complicated. This is also computationally more demanding, because these inversions of the Fisher information matrix that generally scale cubically, so with the dimension. So it is computationally more costly, but through several examples from varieties of contexts, the authors showed that these manifold versions dominates the Euclidean versions of the the Mala and the HMC and random walk and many other algorithms. So yes, they are computationally costlier, but they mixes much faster. Okay. So we see that. So there are a couple of things we can now see that the manifold, we want manifold MCMC algorithms, manifold-based MCMC algorithms, but they also suffer from high computational burden. Another thing as you have already noticed, that these algorithms, not only the manifold versions, but the Euclidean versions also, the naive MALA and HMC, they are not directly applicable to discrete targets, right? They involves derivatives. And there have been a lot of attempts to, develop MCMC algorithms like MALA and HMC variants for discrete targets. In particular, what they do, they generally try to embed the discrete space into a continuous space where they then apply these algorithms and then bring it back. But it has a lot of problems. Again, they are computationally demanding, and also they distort the natural, geometry. Say, for example, the network structure in the discrete space. So those will generally get lost. So let's see. So what do we want? We want a manifold algorithm which are applicable universally to discrete or continuous targets and which are not computationally demanding. Okay. So this is where another Indian statistician, Bhattacharya's idea can be used. And that's what we used, which is, Bhattacharya came up with what is known as the square root representation of the densities. So you can see, so here is the map, Xi map. So it is mapping from the space of densities to M, where it is simply the square root. Okay, but now you can see the square root space it can be thought it is the positive orthant of the unit sphere. So the nice thing about this is that now that I know that the square root space is this this unit sphere, the positive orthant of the unit sphere, I have the exponential map, the logarithmic map, the inverse exponential map, all enclosed from the geodesic distance. That's the length of the arc. So these are all available in closed form. And remember again, I can always take the square to go back to the original space, right? So again, so the idea here is simply this. Okay, so I'll try to make it as simple as possible here. So let's go back. So what was the random walk metropolis algorithm? Random walk metropolis algorithm says if you're currently at X, you draw a perturbation, you basically add a perturbation increment to this X to move to propose your candidate point, right? And this is an Euclidean move. This is a Euclidean move. It's just simply X plus I, but I is another d-dimensional, vector. So it's a Euclidean move, whereas your target lies in a manifold. So it doesn't take into account the manifold structure of your target. So what we plan to do, so suppose we have a normal MCMC algorithm, like say random walk algorithm. So we have a proposal density, the normal proposal density. We are going to move that base proposal density F towards the target according to the the manifold, the geometry, respecting the geometry of the target space. Okay, so this is exactly what we are doing. So suppose we have some k different approximation of the target density pi. So then we are moving the F, the base proposal density, which can be random walk proposal or a MALA proposal. We are moving it towards the target or the approximations of the target according to the geometry of the remaining geometry of the space. So that's the idea. Okay. So now I will. So basically, this gives me the proposal density Q for constructing my metropolis statistics algorithm. So I'll now move to the example of Bayesian variable selection. So again, I'm grateful to the speakers before who introduced the linear regression model. So the notation was y equal to x beta plus epsilon. Here I'm using z equal to x beta plus epsilon. So z is the what is called the response variable, the dependent variable, and x's are the covariates or the predictors of the independent random variables. So for example, z is the house price, and your covariates can be the square footage, the locations, and things like that, right? So the linear regression model is one of the fundamental statistical model, used by scientists all the time, right? That made statistics popular. So here I'm using normal errors, the Gaussian errors. Although for the model building, although this is necessary, but for proofs like which I'm not going to go through in terms of consistency and things like that, you really don't need Gaussian errors. You can go much beyond that. But I will keep it simple. I'll assume Gaussian errors. Okay. Now, so in the talks before, what was assumed that the number of variables was smaller than the number of observations. So the P is less than N. That's the classical context. But as one of the, from the audience, there was a question: when you have many more variables, how do you select? So in fact, you can have situations in the modern science. I'll give you some examples where you have number of variables, P, right? Your number of variables is much, way larger than the number of observations. So P is much larger than number of observations, where you cannot apply ordinary least squares or this classical method. Now there are techniques like penalizations, which are generally used, and I'm going to talk about Bayesian variable selection model, where we penalize the effect size and the model size through some parameters. Okay, so I'm going to introduce. So let me see how much time I have. Oh, okay. So I have around 9 minutes. So we introduce these gamma. It's a p-dimensional vector. So remember, I have p variables, m number of observations, and p variables. So I want to understand which variables are important. So I introduce these p-dimensional indicator vector. So that means this gamma vector, each of these coordinates, gamma is either 1 or 0. So they're all indicators. So 1 indicates that it is important, 0 means it is not important. Okay, so I introduce this indicator variable gamma, and the classical hierarchical Gaussian regression model goes like this. So the first line here, I'm sorry. So the first line is basically that z equal to x beta plus epsilon. I'm writing it this way, but conditional on the gamma. So that is, suppose the given gamma that is given, I know which variables are important. So that those are the only variables which are included in the model. So x gamma beta gamma, x is an n by p matrix. So x gamma is n by mod gamma matrix. So mod gamma is the number of variables which are important. Okay. And then I put on the beta j's, I put normal priors. So this is an example of what is called a spike and slap prior. So here I'm using an exact spike variable which is not important, that is gamma equal to 0. I assign beta j to be exactly 0. So it's called exact spike. And then on the intercept, I have a normal prior. And for the variance parameter sigma square, I have an inverse gamma prior. And for gamma, I basically assume independent Bernoulli, right? So all these indicator variables, I'm assuming they are conditionally independent Bernoulli topos. Okay, so that's the model. Now, so it turns out I can integrate all these parameters in closed form, the regression parameters, the variance parameters, and I have the marginal density of gamma up to a normalizing constant. Okay. Now, so remember again, gamma is a p-dimensional vector, and its entries are either 0 or 1. So that means, so the gamma lies in a space whose cardinality is 2 to the power p. So it's a discrete distribution. Pi gamma given z is a discrete distribution, and it lies on a space where the cardinality of the space is 2 to the power p. And as you can see, with p, it is increasing exponentially, and around p is 79, you already hit the Avogadro's number, right? So if, in fact, more than p30, you cannot do complete enumeration, right? We'll be talking about examples where p is in millions. So you cannot, so, if P is small, you can actually calculate this pi gamma given Z for each possible, choice of this indicator vector and see, which has higher probability, and you choose those variables, right? But you cannot do this in practical setup because P is very large and it's a extremely high dimension space. So what people do, they run MCMC algorithm, okay? A very popular MCMC algorithm is the random walk algorithm we mentioned before, where we use a local neighborhood, move. And this local move is generally consists of one of these moves. It's called addition, deletion, or swap. Addition means, suppose I'm currently at 1, 2. Remember, all I need to know to run the MCMC algorithm, all I need to know how to make one move. Suppose I'm currently at the, I have the variable 1, 2. So those are the only two variables are important, and everything else are non-important. That they are present, and all other variables are absent. So then the addition says just add one of the remaining variables. Deletion says drop one of the current variables, which is basically either the singleton set 1 or 2. Right? The addition set is 1, 2, and J, where J is one of the remaining variables 3 from P. And the swap model is basically you replace one of the current variables with one of the absent variables. So that's the swap model, okay? And then the random walk is basically move is, with some probability vector, which I'm denoting by B, I choose one of these moves. Okay, so these B's add up to 1. So I make a move, from by choosing one of these, right? In particular, many of the MCMC algorithms that people use, in fact, they don't do even consider swap. They just do addition, deletion because of function. But we will be doing all that, and I'll show you how you can do that. So this is the random walk proposal which people are using these days. What our proposal is, we are proposing, this geometric approach, the manifold approach, where we are moving this F according to, along the geodesic to a local approximation of the target pi. And my local approximation target of the target pi is this G, which is basically pi computed among, on all these neighborhoods I mentioned before, the addition, swap, and the deleted models. Okay. Now, so this means I have to be able to calculate all these posterior probabilities, and generally it is difficult. But we, one of my PhD students with my colleague Somak Datta in my department, she developed, in her thesis, a fast Cholesky update method, which we use to actually implement these, and I will show you how you can also use it very easily. So I'll give a one simulation example. I'll give you a reference where there are many simulation examples, but here I'm just going to show one. So here I have M is 400 and P is 10,000. And out of these 10,000 variables, I'm assuming only 5 are important and everything else is non-important, which is generally the case in modern genetics problems. All very few genes, for example, are important. And so there are variants of random walk algorithm in the literature, and I call asymmetric and symmetric versions. I consider both of them, and I consider the geometric variant, the proposed variants of those algorithms also. Okay. Now, so we ran the GMC chain, the proposed chain, only for 100 iterations, whereas the random walk chains we ran for 50,000 iterations, and we repeated these 100 times to basically create this table. So in this table, I have a bunch of columns. You can see here these are different measurements for comparing these algorithms. And I think I'll just since I don't have time, so you can see we reach the true model only in 9 iterations. Only the geometric variants only reach the true model only in 9 iterations, And all these algorithms start with a null model, the same null model. Whereas the random walk chains takes more than 30,000 iterations to reach the true model. And that is also, they fail a lot of time. More than 50% of the time they fail. Okay. So I don't know whether I have time for the real data example. I don't think I have time. But here is a real data example.
Yes, you don't have time. Please finish.
Okay, I'll finish now. So I'll just tell you, give you the reference for the package. So there's an R package called GeoMMC. You can install this R package, very easy. And there is a function called geomc.vs, where you can put your X and Y, the covariant matrix X and the response vector Y, and it will give you, it will run this markup chain for you, and it will produce the important models and a lot of summaries. Okay. Again, that's the end of my talk.
Okay, thank you. Very nice presentation. And any question from the participants? Okay, this manifold MCMC, this is very good. It has high value in particularly in it has when we are dealing with a large number of variables with related variables. This has a lot of applications in genomics, bioinformatics, epidemiology, and in other related settings where we deal with a large volume of data, I mean variables, and with the correlated nature. Only thing is that this has computational cost is very high. Even though this has performance is very high, but computation at the same time, its computational cost is very high. That is the only drawback. Otherwise, this manifold MCMC techniques is largely very highly useful in many fields. Okay, very good work. Thank you.
So just, sorry, you can see here in this example, I have given you the clock time also. So in this example, I have 10,000 variables, and M is 400, which is typically in a plant genomics, you have around, depending on what the panel size, you have around 300 something. So it's only 2.92 seconds.
Okay. Okay.
So I'll just request you to give it a try, this package and this function. The geomc.vs is, this function is for variable selection. Okay. It has other function for arbitrary target, discrete or continuous arbitrary target. So I'll just request you to give it a try.
Okay. Thank you so much. Yeah. Thank you. Very good information.
Thank you.
Over to Sadish, sir.
Yeah, we have an excellent session. We are very much grateful to each one of the speakers. In fact, we are very lucky to have your presentations here in this platform. All are have done a very good, excellent talks, excellent, useful for the youngsters in particular. And we are very much thankful to speakers, especially also we are thankful to the chair, ADM Matthew, for your active involvement in chairing and in chairing the session in a very nice way. Thank you so much. Thank you, Vivekananda Dhoni, Gopal Basar, Shyamala, then NSC Matthew. Thank you so much. We need your.
Thank you.
Thank you. Thank you.
Bye-bye.
Now we can move to the next session. Yeah. Munitra Day is ready to, he's the organizer of the session. I think Pallavi. Fatima?
Sir,
Yeah, Pallavi, please introduce the chair and organizer of this thematic session and support him for the smooth run of this session. Most welcome.
good evening, everyone. Welcome to the 9th technical session, a thematic session of WSTA 2026, 11th International Webinar on Recent Trends in Statistical Theory and its Application. This thematic session is organized and chaired by Dr. Monteta De from Indian Statistical Institute. Dr. De is a distinguished statistician and researcher whose contribution to statistical methodology and multiple hypothesis testing have earned wide recognition in the academic community. We are honored to have Dr. De chair and organize this thematic session. We are pleased to have three eminent speakers with us today. Dr. Montita De from the Indian Statistical Institute, who will deliver a talk on multiple hypothesis testing and dependence. Dr. Anirban Chakrabarti from the Indian Statistical Institute, who will present an interim treatment dropping approach to control type 1 and type 2 family-wise error rates in multi-arm response adaptive designs. Dr. Sayandan Paul from Indian Statistical Institute, who will speak on asymptotic base optimality for sparse count data. All three speakers are highly accomplished researchers, and we look forward to their insightful presentation and valuable contributions to this session. I warmly welcome all participants and now invite Dr. Monteta De to kindly take over the proceedings. Over to you, sir.
Yeah. Can you hear me?
Yeah.
Let me just.
Slide service.
Yeah. So, hello everyone. First of all, I would like to thank the organizers and especially Professor Kumar for giving us this opportunity to present our work here. So, as mentioned by Ms. Pallavi also, so this is a thematic session on multiple hypothesis testing. And so we have three speakers and each talk has the common underlying theme, multiple hypothesis testing. And the first talk is on multiple testing under dependence. So a brief overview. At first, we shall introduce what is multiple hypothesis testing and why this is relevant in today's modern large-scale settings. And then we shall talk about some contributions in the classical fixed sample size paradigm. And then we shall move on to the sequential paradigm. And then we shall conclude with some brief remarks. So multiple hypothesis testing refers to testing multiple null hypotheses simultaneously. So we have n many null hypotheses, H01 till H0n, and corresponding to each one of them, we have one alternative. So the ith null hypothesis is H0i, and the ith alternative hypothesis is H1i. So in a dataset with n predictors, we might be interested to check the significance of each of the predictors. So the ith null hypothesis would be that the ith predictor variable is insignificant, beta I is 0, and the ith alternative is beta I non-zero. Now, one option is that even in those cases, one can test every individual test at level alpha, and then the probability that our methodology is making at least one false rejection is nothing but 1 minus probability of 0 false rejection. And if we assume that the hypothesis or the test statistics corresponding to the hypothesis are independent, so the decisions do not affect each other, then this probability is nothing but 1 minus alpha to the power n. And we can see that for n is equal to 10, this shoots up to 0.4, and for n is equal to 100, this goes up to 0.99. So such high values are not at all desirable, and naturally, we must resort to multiple testing. An applied scenario, a real-life scenario, so DNA microarray experiments, they typically assess the gene expression levels of two populations. For example, the cancer patients and the normal individuals. And the foremost question to ask here is that which genes have significantly different mean expression levels in these two populations. Again, one can use an equality of mean test individually, and one can just record those hypotheses that pass some pre-decided cutoff. But as mentioned in my earlier slide, this leads to inflation in type 1 error. So a multiple testing situation naturally comes in. So what is our framework? So we have n many null hypotheses. Among them, n naught many are true null, n1 many are false null. And depending on the problem in hand, we might have some idea about the relative scale of n naught and n1. So it might be the case in our problem that n1 by n is quite small, say 0.001 or something like that in genomic applications. And a multiple testing procedure, CAPT, is nothing but a statistical decision rule which either accepts or rejects each of the n null hypotheses. So out of these n many nulls, it is rejecting Rn many nulls and it is accepting n minus Rn. And among these Rn, Vn are falsely rejected. So these Vn are actually coming from true null hypotheses, but our test procedure T is actually falsely rejecting those. So Vn is kind of the number of type 1 errors. Now, in multiple testing, there are several notions of type 1 error rates, and two of the most prominent error rates is the family-wise error rate and the generalized family-wise error rate. So the family-wise error rate is defined as the probability that we are making at least one false rejection, and generalized family-wise error rate is the probability that we are making at least k false rejection. So when k is equal to 1, the second one reduces to the first one. And we also know that when n is equal to 1, this family-wise error rate is nothing but our classical probability of type 1 error. So the Bonferroni method is the earliest and one of the most prominent multiple testing procedures. So this suggests testing each individual null hypothesis at level alpha by n. So this is very easy to implement because we just need to calculate the p-values p1 to pn, and we are rejecting the ith null hypothesis h naught I if we observe a value of pi less than alpha by n. So the Bonferroni FW here is the probability of union of this kind of events. Probability of union of pi less than alpha by n, where I belongs to the set of true null hypotheses. Now, Bonferroni has some advantages that it controls family-wise error rate under any dependency among the n p-values, and also it does not require any distributional assumption on the p-values or on the underlying test statistics. However, at the same time, we can see that alpha by n is quite small for large n, and this actually implies that Bonferroni FW would be very small for large n. And this would have some severe consequences, as we shall see later. So this talk focuses on multiple testing under dependence. So why we are actually motivated in testing, in exploring the role of dependence? Because dependence arises quite naturally in many situations. For example, in the many one multiple comparisons problem. So we have one control mean, say the existing drug in the market, and we have in treatment means like the competing new drugs. And we are interested in seeing whether the new drugs, the proposed new drugs, have the same efficacy level as the existing drug, or the proposed drugs are better. So if we use a suitably rescaled version of the differences, then one can see that these test statistics will be non-negatively correlated among themselves. So dependence is quite natural, and the recent literature has witnessed an upsurge in research of multiple testing procedures under dependence. And many of these works have the common empirical observation that classical procedures perform poorly under dependence. But Why so and how much conservative these procedures are under dependence, this is not well understood. So this is our motivation. So the existing literature lacks a systematic study of the performances of family-wise error rates or the generalized family-wise error rates controlling procedures under dependent setups in the fixed sample size and sequential paradigms. And now we shall focus on some works we did in this direction. So at first we shall focus on the fixed sample size paradigm. So what is the framework here? So we have n observations, x1 up to xn. Each of them is coming from a normal distribution with mean μi and variance 1. And these statistics x1 to xn, these are jointly multivariate normal. So one might assume the correlation structure is equicorrelated. That is, correlation between xi and xj does not depend on I or j, or correlation between xi and xj depends on I or j, but it is non-negative. So, or one can assume other correlation structures as well. So what is the problem of interest? So we are interested in testing whether the mean of the underlying distribution is 0 or whether it is strictly positive. So we are in the one-sided setting. So again, we have n observations, n test statistics, x1 to xn. These are coming from a normal distribution with mean μi and variance 1. And under the null, μi is 0. Under the alternative, μi is strictly positive. So this is the problem. Now, Dash and Bhandari considered this equicorrelated setup, and they showed that asymptotically, this Bonferroni FWR is a convex function in the equicorrelation row. So here in this plot, on the x-axis, we have the correlation parameter row, and on the y-axis, we have the FWR. Now, this green, red, and blue respectively denotes the FWR values for n is equal to 1000, n is equal to 10,000, and n is equal to 1 million. So you can see that as the number of hypotheses increases, the convexity nature becomes more and more apparent. And as an immediate consequence, what one obtains is that the Bonferroni FWR is asymptotically upper bounded by this straight line. That alpha time, so it is upper bounded by alpha times 1 minus rho as n tends to infinity. So, for example, when rho is equal to 0.5, Bonferroni is actually controlling FWR at level alpha by 2 asymptotically. And this is being very conservative. So this corollary gives an estimate on the asymptotic conservativeness. Now, this is a problem because Bonferroni, as we also mentioned earlier, is one of the most widely used multiple testing procedure, and it controls family-wise error rate under any dependence. However, it is very conservative for large values of n. And several related problems arise. For example, this is only an asymptotic upper bound. Can we find some non-asymptotic upper bounds? Those bounds will help us see the extent of the effect of dependence under small or moderate dimensions. And can we find some non-asymptotic bounds on generalized family-wise error rates? And can we find the asymptotic limit of this Bonferroni FWR? So at first, we consider the problem of having a bound in the general non-asymptotic case. So we see that when n is equal to 100 or n is equal to 500, the alpha times 1 minus rho bound is no more valid. And at the same time, we cannot proceed in the same direction as the earlier work because they had n tends to infinity. So they resorted to asymptotic techniques and dominated convergence theorems and so on. But we have n to be small or moderate dimension. So we cannot proceed in their same direction. But we observe that Bonferroni FWR is nothing but the probability of union of suitably defined events. And using this fact, we utilize some probability inequalities to obtain an upper bound on the Bonferroni FWR. And this upper bound works for any n and any sigma n having non-negative entries. So we now move to generalized family-wise error rates. So it is the probability that we are making at least k false rejections. So if so Lehman and Romano in their 2005 paper say they defined k family-wise error rate as the probability that pi is less than equal to k alpha by n for at least k i's such that the corresponding null is true. So if k is equal to 1, this procedure is nothing but the Bonferroni procedure. So Lehman-Romano procedure is an extension of the classical Bonferroni procedure. So here we can see that this KFWR is nothing but probability that at least k out of n events occur. And here we propose a new inequality, a new probability inequality. So if a1 to an are n events, then for all k, the probability that at least k out of n ai's occur is less than equal to this quantity. And this quantity is a function of the sum of individual probabilities, the sum of pairwise intersection probabilities, and the maximum of those sum of pairwise intersection probabilities. So this generalizes some existing results in the theory of probability inequalities, but this gives rise to an improved upper bound, and which in turn results in an improved multiple testing procedure. For the sake of time, we shall not discuss the improved multiple testing procedure in more technical detail, but we shall elucidate its effectiveness through a real data set. So we have a prostate cancer data set of around 6,000 genes for 102 individuals. Among them, 52 are prostate cancer patients and 50 are healthy persons. And our goal is to identify those genes whose levels vary between these two populations. So H0 I is the null hypothesis that expression level of gene I has same distribution for normal and cancer patients. Now, this table summarizes the performance of the Lehman-Romano method and our proposed method for a series of values of k. So we can see that our method is actually making much more rejections than Lehman-Romano method while still controlling the family-wise error rate, the generalized family-wise error rate less than equal to alpha. So now we move to the asymptotics part. So here we show that the Bonferroni FWR is asymptotically zero under any configuration of true and false null hypothesis. And this is under any general dependent structure for which limit of the correlation is strictly positive. So here we are allowing negative correlations as well, but only finitely many negative correlations. So if we consider k as a function of n, and if kn is equal to small o of n to the power delta, where delta is this limit of the correlation, then we have shown that Lehman-Romano method has this problem as well, that asymptotically, the kn FWR, the generalized family-wise error rate of the Lehman-Romano method, that is also zero. So asymptotically, Bonferroni family-wise, Bonferroni or Lehman-Romano method, they do not make any rejection at all. Now we move to a separate class of multiple testing procedures which are more powerful and which often are more rejective. So at first we are ordering the p-values, p order 1 up to p order n, and we are denoting the corresponding null hypothesis as this, H bracket not I. And we are considering this set, Sn is the set of all n tuples in Rn such that the first element is less than the second element is less than the third, and a p-value based step-down multiple testing procedure uses a vector of cutoffs u, where u lies in this set, and rejects a hypothesis H0 I if and only if p order j is less than equal to uj for all j less than equal to I. So here we are focusing on a new class, step-down multiple testing procedure. So at first, this compares the most significant p-value is the minimum p value, p order 1, with the smallest u value in our set u1 at first, and so on. So if m1 is the maximum over all such i's, p order j less than equal to uj for all j, then the step-down multiple testing procedure rejects those first M1 many null hypotheses. And a classical example is the Holmes method, which is also in some sense the optimal step-down multiple testing procedure. So this rejects the ith null hypothesis if p order j now down multiple testing procedure. So it says that asymptotically, any step-down multiple testing procedure does not make any rejection at all. So any step-down procedure does not make any false rejection. So family-wise error rate is 0, and it does not make any true rejection. So its power is also 0. So if we have dependence and if we have a large number of hypotheses, then step-down methods are not going to help us. So now we move to the second paradigm of this talk, the sequential paradigm. And now we move our notations. So from now on, n is the sample size and k is the number of hypotheses. So we have k data streams, stream 1, stream 2 up to stream k, and stream 1 is the first row, stream 2 is the second row, and stream k is the kth row. And we assume that these columns are generated independently. So the first column is independent of the second column, and the second column is independent of the third column. So it is the observations are arising in an online manner. And also but for each j, this vector is an k-variate multivariate normal with equicorrelation structure having correlation parameter rho. So we have a k-dimensional multivariate normal, and we have sequential observations from that. And the underlying testing problem is that whether the ith row is coming from a normal with mean 0, or whether the ith row is coming from a normal with mean mu, where mu is strictly positive. So here, as in the classical sequential setup, we can control two types of error rates simultaneously. So the family-wise error rate of type 1 and the family-wise error rate of type 2. So the first one is the probability that rule makes at least one false acceptance. Now, we have also considered other setups, but in this talk, we shall focus on this case where we already know beforehand that what is the cardinality of the set of true nulls and the set of false nulls. So we assume that from this k many null hypothesis, exactly m many null hypotheses are coming from the alternatives, and k minus m are coming from the true nulls. So our proposed rule is based on the cumulative sums. So we record the cumulative sums, and then we propose this stopping time. So since we know beforehand that m many are coming from normal mu1, and if we collect observations again and again, it is intuitive that the top m cumulative sums will correspond to the true alternatives with high probability. So we are observing this difference between the mth order statistic and m plus 1th order statistic of these summation values. And when this difference is very large, then we are stopping, and then we are rejecting the top m many hypothesis. And we have shown that as alpha and beta tends to 0, this procedure, this sequential procedure, is asymptotically optimal in the whole class of procedures. And this is asymptotically optimal in the sense that the average sample number of our proposed rule and that of the classical sequential probability ratio test, the SPRT, goes to 1 asymptotically. So here we have simulations. So we have 20 data streams. Among them, so the signal is present in 3 streams and mu I is equal to 0.5. And without loss of generality, we are taking alpha is equal to beta. And we have rho is equal to 0.1 for the blue line, rho is equal to 0.5 for the red line, and rho is equal to 0.9 for the green line. So we can see that as alpha tends to 0, the average sample numbers tends to increase, and for greater values of rho, the average sample numbers is less. And this is also intuitive because rho hello. Any question? So if there is no question, then we can move to the second talk of this session. So the second speaker is Mr. Anirban Chakraborty from Indian Statistical Institute, who is going to present his research on controlling family-wise error rates in multi-arm response adaptive designs. So Anirban, the floor is yours.
Thank you. Good evening, everyone. So can you hear me and can you see my presentation?
Yes, Anirban, we can hear you.
The title of my talk is an interim treatment routing approach to control type 1 and type 2 family-wise error rates in multi-arm response adaptive designs. This is a joint work with my PhD supervisors, Professor Samal Krishna and Professor Atanu Vishwas. So we consider a clinical trial experiment with M experimental treatments and a common control. Our objective is to select the treatments which are better than the control and which are worse than the control. Such study now being popular because it saves time and resources compared to conducting separate M clinical trials. Why response adaptive designs? In clinical trial, usually patients come sequentially and they are allocated to the one of the competing treatments with equal probability. But in clinical trials, since human beings are involved, therefore we need to address the ethical concern along with the statistical precision. To this end, response adaptive designs are used to trade off between the statistical precision and ethical aspects. The goal of response adaptive designs is either to increase the probabilities of randomization to the better performing treatments or to minimize some appropriate cost function with respect to some suitable constraints. Usually, the cost functions comes from the ethical aspects and these constraints come from the statistical precision. We shall see later in details. The problem like this, for each individual, we can have M+1 potential responses based on which treatment is being allocated to that individual. We are assuming that for each treatment, the responses are distributed. FL distribution function is FL with mean mu L and variance sigma L square. Now, to select the treatments which are better than the control, we consider this following M simultaneous testing. If we assume that larger mean implies better treatment, then this lead to this simultaneous testing problem that mu I minus mu naught less than equal to delta naught versus mu I minus mu naught greater than equal to delta 1. Here, delta naught is marginal improvement and delta 1 is the clinically significant improvement. in multiple testing, the type 1 error is defined as probability of at least one false rejection, and type 2 familiarized error rate, which is called FWR2, that is defined as probability of at least one false acceptance. In response adaptive setup, recently Robertson and Watson developed a procedure to control type 1 FWR, but in very specific setup, that is for Gaussian distribution and with homoscedasticity and known variance. But they controlled the exact, they could derive the exact control. And they and Baron developed some procedures to control FWR1 and FWR2 simultaneously. But their procedure was likelihood-based procedure. That is, they assumed some distribution, and based on the likelihoods, they developed their procedure. And also from their procedures, what should be the actual allocation rule or optimal allocation rule, it was not clear. So here in our work, we are developing a procedure to control FWR1 and FWR2 at these specified levels, and to propose an appropriate response adaptive setup to minimize a reasonable cost function. Start with the Bonferronis approach. Suppose n individuals are allocated to the competing treatments, among them NLN allocated to the LF treatment, and the corresponding mean for the sample mean for the LF treatment is X bar L. So we assume that test criteria that the difference between the sample means and the sample mean of the control and sample mean of the IF treatment is greater than a prefix constant. Why we are calling this Bonferronis approach? Because the cutoff is constant here. Now, using Bonferronis inequality, and if we assume that NLN is sufficiently large for all of the treatments, then we get an asymptotic upper bound of familiarized error rate 1. And similarly, we can get an upper bound of familiarized error rate. Now, to control familiarized error rate 1 and familiarized error rate 2 at level alpha and beta, then we take these quantities. Take these quantities is less than equal to alpha by m, and these quantities is less than equal to beta by m. By these two quantities and considering equalities, we get a closed value of C, which looks like this. And if we put C in these inequalities, we get the constants on the sample size. And following this, we consider an allocation rule which minimizes summation NLN psi L with respect to those m constants on those sample sizes. So psi L may look like probability XUL less than H, because XULs we are assuming that the treatment means are greater than treatments are better. So responses are less than H. We are assuming that the treatment then fails. So it minimizes the expected number of treatment failures. And if we assuming that psi L equal to 1, it minimizes the total sample size. So Bissas et al. Derived the optimal allocation proportion for this allocation rule, but they didn't derive this allocation rule from the viewpoint of the familiarized error rate. They got the constants from the viewpoint that the asymptotic variances of those treatments, difference between the sample means bounded by a prefix constant. So using these allocation rules, we get the oracle optimal sample size in this form. But here we can see that all the parameters are unknown. So NB stars will never be known. So we have to develop a sequential procedure to estimate NB star and finally to derive the test rule. So we call it response adaptive allocation with interim dropping Bonferronis procedure. Suppose based on n observations, we have strong consistent estimator of psi L and sigma L square. And plugging in psi L and sigma L, the estimated values of psi L and sigma L square, we can get the strong consistent estimator of pi L. And we are assuming that based on the n observations, the current number of active treatments are denoted by script n. So we begin the trial with K patients for M experimental treatments and the control. So at the beginning of the trial, we have the active set contains all 1 to m. So at stage 1, after n greater than equal to n naught, to allocate the n plus 1th individual, we generate a discrete random variable u, which takes value l with probability pi hat n. We stop at t1 for first time when these inequality constraints or these conditions are satisfied. This comes from the data-driven versions of those constraints we got. And we drop those treatments for which the inequalities are satisfied. That if these inequalities are satisfied means actually sufficient information for those treatments has been collected. So we can drop those treatments and take decisions for those treatments. So we at T1 we update the set of active treatments and reject those H naught I if and only if at T1 the difference between the sample means greater than that earlier derived C. At stage R, suppose at the beginning of the Rth stage, the active set is I1, I2, and IMR. And for n greater than equal to TR minus 1, we update the allocation proportions as the following way. Looks like the similar things, just the L belongs to the active set, not remains the 1 to M. Similarly, we stop at where the sufficient informations are collected for some of the treatments, and we drop those treatments for which selected, and we take decisions for those treatments. We move to the next stage if the active set is non-empty, and if we stop if the active set is empty. It means that our final stopping time is asymptotically equivalent to the Oracle optimal size in V star. And we have shown that if the second moment of FL is final, power plus O1 and FWR2 less than equal to theta plus 1 as delta tends to 0. Delta tends to 0 means when null and alternative are almost indistinguishable, then also our procedure can distinguish null and alternative with controlled FWR1 and FWR2. So we know that the Bonferroni's procedure is conservative and the inequality is good. So we improve this procedure by the motivation of Holmes' idea. So based on the responses of n individuals, we arrange the sample means in decreasing order, and their corresponding sample variances are S on 1 square, S2 square, and Sn square. So we define the new ordered cutoff as these things. Here, alpha by m is replaced by alpha by m minus I plus 1, and beta by m is replaced by beta by I. It's completely motivated from Holmes' idea. And we define new constants where for Bonferroni's constants, alpha by m is replaced by m minus I plus 1, and beta by m is replaced by beta by I. We propose a similar allocation rule which minimize summation NLN psi L subject to those newly defined constraints. And consequently, the Oracle optimal size looks like this, but here the allocation rules have no closed form solution. So it will be a numerical solution. Here also all the parameters are unknown, so we have to propose an sequential rule to estimate this NH star and consequently the test rule. So we see here also the definition of active set is same, and we have the strong consistent estimator of psi L and sigma L square. So here for n greater than equal to n0, we at each stage we arrange the sample means in decreasing order, and at each stage we set up these constraints and we find the optimal solution. From the optimal solution we get the allocation rule, and by generating a discrete distribution, we allocate the n plus 1th individual to one of the competing treatments. And we stop for the first time at W1, which is defined, looks like this, and these are this data-driven version of these constraints. That is, at W1, for some of the treatments, sufficient information has been accumulated, and we drop those treatments for which information has come, and we take decision for those treatments. The set of drop treatments at W1 can be defined is, and we reject H naught I if and only if X bar I at W1 minus X naught bar at W1 greater than Ci. And stage R is similar. The active set is updated as I1, I2, IMR, and for n greater than equal to WR minus 1, we ordered the sample means, and the rank is assigned from those indexes which present in the active set. So similarly, we estimate the allocation proportion at each stage, and by generating a discrete distribution, we allocate the patients to one of the active treatments or control. And similarly, we stop at WR, which is defined as this. Point 2 and different values of delta naught and delta 1. Here also we see that the rate procedure is the best procedure in terms of producing the smallest average sample number and the smallest expected treatment failures. And we similarly see that the Holmes procedure performs better than Holmes. So we have developed a new response adaptive randomization framework for multi-arm clinical trials that allows experimental treatments to be discontinued as soon as sufficient evidence has come. And building upon this treatment dropping strategy, we have proposed two new multiple testing procedures to control FWR1 and FWR2. And the interesting point is our procedure do not need any distributional assumption. For any distribution, we can use this procedure. And for future work, we are considering a problem of how to incorporate the patient level characteristics for the treatment allocation and decision making. When in treatment allocation, we use the covariate information, then the simple average, the difference between the simple average can no more estimate the actual treatment effect. It becomes actually inconsistent. And another problem becomes how to extend the methodology to survival studies with censored outcomes. When some of the observations will be censored, then our procedure will not work. So these two problems can be a beginning of the future work. These are the references. Thank you.
Thank you for the nice talk, Anirban. Any question? So if there is no question, we thank the speaker. It was a very well-organized talk. And then we move to the third and last speaker of this session, my dear senior Shantanda, who is now an assistant professor in Dhirubhai Ambani University, and he will present his research on multiple testing from a Bayesian point of view.
First of all, I want to thank Professor Kumar and the organizing committee for giving me the opportunity to present my work. And also want to thank Dr. Pallavi and Dr. Dey for this nice introduction. So without wasting too much time, now I am going to talk about the topic that is asymptotic base optimality for sparse count data. And this is one of my work done during my PhD under the supervision of Professor Arijit Chakraborty. And so this is a brief outline of the talk. So first, in the few slides, I will talk about what is the problem in which we are interested and the literature review regarding that. And since this is from a Bayesian perspective, I will incorporate two different types of prior, one named as two groups and another is one group prior, and some theoretical results corresponding to that. And next, through our simulations, we will try to see that to what extent our theoretical results have some simulation example, and then I will illustrate and real data analysis and end with our contributions. So in today's world, as we all know, we are in high dimensional era where the number of observations n and the number of parameters p both grows to infinity. Multiple hypothesis testing has been a growing area of research. And one of the main reasons behind that, it has a wide area of application starting from genomics, bioinformatics, economics, finance, and many more. And we, as you all know, the multiple hypothesis testing area come into the literature in the broad sense after the work of Benjamin and Hochberg for their false discovery rate control. And after that, several works and several authors like Benjamin Equitelli, J.D. Story, Shonat Sarkar, Chen and Sarkar, and Bodan et al., and many other authors also have shown interest in studying problems related to multitasking in both frequentist and Bayesian viewpoint. However, all the works that I mentioned in the earlier slide are based on the famous sparse normal means problem. So what is normal means problem? Suppose we have an observation vector x car, x1, x2, xn, where each xi is modeled as normal distribution with mean say theta I and variance some known say sigma square, and we are interested to test which of the theta is are 0 versus which of them are not. This is termed as the normal means problem and the area of multiple testing. On the other hand, there is now a literature on the growing area of the multiple testing where we have quasi-sparse count data present. That means we are actually interested about some events where the number of occurrences of that events are either 0 or close to 0 in most of the cases. However, there are some situations where the number of occurrences is quite large. And in this case also, like other multiple testing scenario, the main target is to figure out the real signals from this pool of noises. To give an example to this real life situation, so suppose we are interested about figuring out the crime rate, number of crimes in an area, and what situation we'll see in most of the cases that in most of the regions, the number of occurrences of a crime is quite small or moderate, but still there are some regions which are actually crime prone. So if from the Bayesian perspective, we want to model this situation, we will have a prior which has the dual nature of simultaneously switching this noise observation towards 0 along with so if we want to model this situation in from a Bayesian perspective, our prior should have the dual nature of simultaneously switching these noise observations towards 0 along with keeping the large observations in intact with the assumption that we have the level of sparsity which is present in the situation to be kept. And if we want to present it in the way of our statistical point of view, so suppose we have an observation vector y card y1, y2, yn, where each yi is modeled as Poisson distribution with mean say theta I. And in this case, both the theta vector theta 1, theta 2, theta n is the parameter of our interest. And we are actually interested in the sparse asymptotic region where the sample size n is large and the number of proportion of non-null is quite small. So since we have already a dichotomousness in these theta i's, so in order to model this situation, one can actually think about using a latent variable uy, which uy is actually nothing but a Bernoulli random variable with success probability as p. And this nu I can be incorporated with the hypothesis, with the event of the hypothesis, say h naught I, in the sense that nu I equals to 0 is same as happening that h naught I is occurring. On the other hand, nu I equals to 1 implies that h1I is happening. So we want to think this hypothesis testing problem, simultaneous testing problem, as testing about nu I equals to 0 against nu I equals to 1. And based on this situation, since we are thinking a table testing problem and we have the usual 0 and loss function if we consider, so the first question that comes into our mind is that what will be the expression for our base risk to be as minimum as possible? Because for any testing situation or any multiple testing situation, we always want to minimize our base risk. So the question that automatically comes to our mind is that what will be the expression for the optimal base risk. And the second thing is that suppose we are interested about performing, or we are interested about conducting or a multiple testing procedure based on some continuous priors. Can we guarantee that this multiple testing procedure will be ABOS? Now, why the continuous prior we are thinking about, I will tell it later, but what is ABOS, I am going to tell it now. So multiple testing rule, asymptotic base optimality under sparsity, on short ABOS, is defined is this way. So if you calculate the base risk of the multiple testing rule to that of the optimal rule, and if these two ratio converges to 1 under the asymptotic framework introduced by Bodan et al., then this multiple testing rule is termed as ABOS. However, this work of Bodan et al. Is on the work of the normal means problem, and we are interested about quasi-sparse count data. So we are interested whether we can think about a multiple testing situation or a decision rule based on multiple testing procedure using a continuous prior, such that this ABOS property can be established for the quasi-sparse count data. Now, as this is a Bayesian flavor, so next I am going to introduce the two groups and one group's prior. So since there is actually a sparsity present in that case, so the first work in that context was done by Michel and Beauchamp, where they incorporated spike and slab prior, which is actually a mixture of direct measure at 0 with probability 1 minus p and a heavy tail distribution, which is required for capturing the large values of the data set, and it is coming from a distribution with probability p. So an example in the Poisson context is that we can take this heavy tail distribution as gamma, and how that was first work done by Datta and Danson, where they modeled this each theta i's as a scale mixture of two gamma distributed random variables. So theta I is IID with 1 minus p probability, it is gamma alpha beta, and with p probability, it is gamma alpha beta plus delta. Now, these alpha, beta, and delta, these three are hyperparameters. So our target is to choose these hyperparameters such that we can actually have a heavy tail distribution in the alternative and compared to the distribution which is present in the null. Now, this can be done in this next step. So keep the shape parameter alpha to be fixed and let beta goes to 0. So what will happen? Since we know that for gamma AB, the mean is AB and variance is AB times B plus 1. So for the null distribution, it's both mean and variance will go to 0. And as a result, using the Chebyshev's inequality, we can see that this distribution will actually have its mean and variance going to 0. That means it will be degenerate at 0. On the other hand, if we take delta to be large compared to beta, then it's both mean and variance having of the order of delta and delta square, and as a result this will be far away from the null distribution, and as a result we can actually will not have any problem regarding the identifiability corresponding to this setup. Now if we are now recall that the first problem that we are considering, or the first question that we want to answer, was what will be the expression for the optimal base risk. And in order to study that, first we have to go to the marginal distribution of yi, which is actually in this case a convex combination of two negative binomial distributions. And in order to figure out what will be the decision rule, it can be actually done in quite a simple manner, in the sense that if we want to minimize the base risk, it will actually eventually lead to this following decision rule. So first we have to calculate the likelihood of the ith alternative to the ith null, and we have to check whether it exceeds 1 minus p by p. Or in other words, the optimal base rule will reject the ith null if yi is more than c, where this c is actually a function of p, alpha, beta, and delta. Now remember that this decision rule actually depends on all of these hyperparameters, or all of these parameters which are actually unknown. So if we keep the sample size n to be fixed, after that we cannot do any theoretical justification or any theoretical study of this decision rule. And that's why first we have to keep our decision, first we have to take our sample size n towards infinity. And that's why the term asymptotic base optimalities, the asymptotic terms comes into picture. And along with the assumption with the sample size n going to infinity, we also need the delta to be fixed, and because along with the sparsity level p to be going to 0, because we are considering a sparse situation, and also the beta, the scale parameter corresponding to the null distribution, that is also has to go to 0 because of its kind of concentration towards the origin. And since both beta and p goes to 0, since both beta and p actually goes to 0, we need a relative rate of beta by p going to 0. That's why we need beta going to 0 faster than p. And based on these two sets of assumptions, we can actually have the upper bounds of the error risk, the type 1 and type 2 error of this following form. And it can easily be shown that of these two type 1 and type 2 errors, the type 2 error is the dominating term, and that actually results calculating the base risk of this decision rule, which is of this form. So this gives the first answer to the question that what will be the expression for the optimal base risk. Now we are moving towards the second question, that can we think about a decision rule using the two groups prior such that using continuous prior such that these kinds of above property can be established. So why the one group prior is actually required? Now we come into that part. So since there is a dichotomousness in the thetas, so it is quite natural that the two groups prior will actually be quite intuitive in modeling this situation. However, from the viewpoint of a computational, it is quite prohibitive because since the theta is a dichotomous, if we want to draw samples from the posterior distribution, the corresponding Markov-Chain Monte Carlo actually becomes quite unstable. Actually, it actually hits to the local maximum, not the global maximum. And since the drawing the posterior samples is actually drawn using the highest posterior probability region, so always we cannot guarantee that we will get the best possible result. And as a result, people from the last decade start to think about priors which are actually continuous in nature, such that we can have the flavor of the two group structure in our one group familiar pattern. And some examples of these one group priors are like the T priors due to tipping, the Laplace prior of Park and Casella, the normal exponential gamma prior of Griffin and Brown, the horseshoe prior of Carvalho, and 3-parameter beta normal of Armageddon et al., and generalized double Pareto, and like that. So now I will talk about the one group priors and its literature corresponding to the count data. So the only work in this context is due to Dutt and Dunson, where they modeled the one group prior in this following format. So they incorporated two hyperparameters, lambda I and tau, and given lambda I and tau, so theta is generated from a gamma distribution with shape as same as alpha and the scale parameter as lambda I squared times tau square. And for lambda I square tau square, they had some other priors. But before going to that, remember that this lambda I actually varies with each theta I, and that's why this lambda I is termed as the local shrinkage parameter. On the other hand, this tau is fixed throughout this hierarchical formulation, and that's why it is termed as the global shrinkage one. And for the prior distribution of lambda I square, they actually used a remodeling of that in the sense that they reparameterize this lambda I square as by kappa I, which is defined as 1 by 1 plus lambda I square times tau square. And they modeled kappa I using a Gauss hypergeometric prior of this form. However, motivated by the earlier works of Ghosh et al. Regarding the normality assumption, the sparse normal means model, we in this work consider a broad class of global local priors, which is actually modeled in this form, where this k is actually the proportionality constant, and this L is actually a slowly varying function, which is defined in this way. So for any alpha positive, if L of alpha x by Lx goes to 1 as x tends to infinity, then we call this L to be a slowly varying function. And why I am calling that as a broad class of prior? Because for different choices of A and different choices of L, we can actually have all of these priors as a byproduct of our general class of priors considered. For example, if you take A to be half and LT to be T by 1 plus T, you will have horseshoe prior. On the other hand, if you take A to be the same thing, not as half in general A, and LT as T by 1 plus T to the power A plus U, you will have 3 parameter beta normal. On the other hand, for the hypergeometric inverted beta, if you take that LT to be lambda squared to the 1 plus 1 by lambda squared to the power minus a minus 1 times this quantity as the L slowly varying function, you will have all of these pairs in our general class of pairs considered here. So that's why I am calling it as a general class of pairs. So this is in general hierarchical formulation, just to give to summarize what I have talked till now. So our hierarchical modeling is like that. So given theta I, yi is actually generated from a Poisson distribution, and theta I given lambda I and tau is generated from a gamma distribution with parameters as alpha and lambda I squared times tau squared, and then lambda I squared is modeled in this following format. Now, regarding the choice of tau, we will actually consider two cases, and when the level of sparsity, that means the number of alternatives or the number of known nulls that is known to us, we will use tau as a tuning parameter, and when it is unknown to us, we will use an empirical based estimate corresponding to that. Okay. So, do you have any question till now? Do you have any question? No, I will talk later. I am asking that till the talk. Do you have any question?
Anyone has question? Any
Okay.
clarifications required, please? I hope there is one.
So I will continue.
So, so the organizer of the session can give an outline of the or something you have to say about the session topic, useful for how it is useful for the youngsters or new researchers.
Can you tell again?
Yeah, how I have to conclude this session because all the three speakers
Yeah. I
over,
will go
isn't it?
towards the application. I will go towards application. I was asking that is there any question till now?
Yeah.
After that,
Okay.
I will go
Okay.
towards some theoretical results and
That's fine.
application.
That's fine.
So I will move towards that section. Okay.
Yeah. That's fine.
First, I go towards some theoretical results and then towards the application. So first, in order to study the one group pairs, whether it can achieve that optimal base risk, first we have to formulate a Rishan rule. So in this Rishan rule actually can be formed in this way. So we will reject the ith null if the posterior mean of 1 minus kappa exceeds delta by 2 times delta plus 1. And this is actually obtained by comparing the posterior mean of theta I when it is modeled by one group and by two groups pairs. And for the sake of completeness, I have written here, since this depends on the L function, which is actually in general. So for the theoretical study, we need some assumptions on L, and we have these two assumptions, which actually means that L is both bounded away from 0 and infinity. And based on these two assumptions, the first two results are quite important. So the first result says that when the observations are quite small in this range, so yi is in 0 to some a minus 1 with a more than 1, then the posterior mean of 1 minus kappa I can be bounded by this form. And see that if this tau goes to 0, that upper bound also goes to 0. That means if the observations are not too large, if the observations are 0, that will be kept in intact. So the two basic properties that the one group prior should have in the Cauchy-Sparse count data to match to some extent to the two groups, that is actually established by these two results. However, our result was related to the base risk, and for that first we have to obtain the type 1 and type 2 errors, and the type 1 error can be actually bounded by this form. So it is bounded by alpha beta by a minus 1. On the other hand, the type 2 error can be bounded by this form. So it is probability of y less than a quantity, which is 2a plus alpha minus 2 times a plus alpha by delta plus 2, where this y is actually a negative binomial distributed random variable. And these two results actually imply us that if we are interested about the ratio of the two risks, the Bayes oracle and the risk corresponding to one group pairs, these have a result in the sense that its lower bound is always 1 and we have an upper bound related to that. So the question next comes to that. So how large this upper bound can be? We will see that in our simulations. But before going to that simulations, here see that we have an assumption in the sense that our the global parameter tau that has to go to 0, but we have another assumption that the tau and p, the level of sparsity, that has to be in the same setup or in the same asymptotic region. And p is the proportion of non-null, which is actually unknown in most of the cases. So if the p is non-null, then we cannot use the previous result. That's why we need an empirical based estimate of tau in order to tackle this situation. And motivated by the work of Iano et al., where they proposed an estimate of the number of non-zero means SA as this form, we express an estimate of empirical based estimate of tau, and using this empirical base, our decision rule now modifies to this. So previously it was posterior mean of 1 minus kappa given ya and tau. Now instead of tau, we have the estimate of tau. Now remember that though these two decision rules behave similarly in this form, but there is quite a huge difference in the sense that this decision rule, this tau hat actually depends not only on yi but on all the other observations also. But on the other case, when the tau was a global shrinkage parameter is tuning, that already depend on yi. So it is not necessarily
Now
that
you can.
these two decision rules are going to behave similarly. That's why we will study about
Good
these
morning.
empirical based versions, whether it can achieve the same kinds of risk bounds or not. And for that case, again, we have obtained the expressions for the type 1 and type 2 errors. So the expression for the type 1 error, we have an upper bound related to that. And for the type 2 error, we have an upper bound, which is of this form. And this upper bound is also exactly same as that was obtained for
Okay,
the
so the
female
thing is-
case. And since this of these two type 1 and type 2 errors, actually the type 2 error is actually dominating. This actually results in the upper bound to be of this form, in the sense that both the upper bounds, both the ratios of these upper bounds is actually, again, though depends on delta A and alpha, but still have the upper bound to be same.
Hi,
Now
good
we want
morning.
to study in our
Good morning to you.
simulations that
Yeah,
to
good
what
morning,
extent these values are.
Now
But
I've got to
before
find
going
the,
to the simulations, the study is related to the convergence or the shrinkage coefficients. So remember that the first two results, we showed that when the observations are small, the shrinkage is towards 1. When the observation is large, the observation is small, the shrinkage is towards 0. When the observation is large, the shrinkage is towards 1. And we'll try to see that the same thing happens in this case also. So here we have taken 200 observations. Of them, 80% are from the null. That means true values are 0. And the remainings are true values. Some of them are 2, 3, 4, like that. And we expect that for their posterior means is also going to be similarly. And the main thing is that for the shrinkage. Now, for the observations which are small, their shrinkage is also going towards 0. And the observations which are quite large, their shrinkage is actually more than 0. And it's almost 0.5 to 1. And that actually gives us some intuition that our priors is going to behave similarly two groups prior. That is usually the gold standard in this context. And next, motivated by this, we actually done the simulations corresponding to the miscalculation problems based on 1000 replications. So we are going to the sparsity level from 0.01 to 0.2, and we are going to compare the misclassification probabilities of the two groups prior with a particular candidate of the one group as the 3-parameter beta normal, with both using tuning and empirical based approach. And also we are going to compare that with the work of Dr. Dunson, where they use the Gauss hypergeometric prior. So what we can see that when the sparsity level is quite small, like related to 0.8 or 0.9, the two decision rules are quite similar to each other. On the other hand, even if the sparsity level is related to 0.18, 0.9 up to 0.2, then also the ratio is not exactly 1, but still it varies within 1.3, 1.4 like that. So though our theory does not directly imply that the upper bound is actually quite close to 1, but through simulations we have an intuitive justification that the upper bound is not too much. And motivated by this, actually we do a real data application where we calculated, where we have the data for the global terrorism database from the years 1970 to 2020, and the red lines actually denote the true values and the green line denotes the estimated values using 3-parameter beta normal, and the blue lines estimated values using Gauss hypergeometric prior. Now see from this picture that when the observations are actually quite large, for example, in the order of 100 to more than that, the red and the green and blue lines are quite similar, and that's why you can only see the blue line, not the green line. But when the observations are moderate, in the sense that the observations are in this case, there the green line, the values are almost equal to 0. On the other hand, our estimates actually giving much better than the existing results, and that's why for the moderate cases our values are quite better, or there are some situations when we can say that our method is going to get better result than some of the existing works already present in the literature. And now I will briefly mention about the contributions to the in these slides. So there are mainly three contributions. First of all, that depending on the proposed model of Dutt and Danson, first we have obtained the expression for the base risk corresponding to the two groups prior, and what will be the optimal risk. Next, depending on the level of sparsity to be known and unknown, we have obtained a decision rule based on one group priors, and we have shown using theoretical results and simulations that this rule also attains the optimal base rule up to some multiplicative constant, and that's why it's kinds of near atoms, and that is the thing. So these are some references, and so this is the work of Dutt and Danson that I was mentioning, and this is our work on which the slide is presented. And thank you. So if you have any question, please ask.
Any questions? Hello, can you hear me?
Yes, sir.
Okay. Pallavi,
Yes, sir.
okay, you can, if there is no questions from the audience, you can conclude the session. What about, before concluding, the organizer, can you say you want to add anything more?
Yes, sir, you were asking about,
Monitor?
like, yeah, sir, in between you were asking about, like, why is multiple testing relevant? And I would like to mention that multiple testing is an area of statistics which has interesting theory and also important applications. And one of the beauty of this field is that it does not have one size fits all solutions till now. So some methods which are going to work in genomic applications very well, those are not going to work that much well probably in neuroimaging applications. So there are theoretical challenges, and there are also, like, since we are talking about several variables and dependent structures, and also we deliberately wanted to keep this session as varied as possible. So, so each of the three talks had the common underlying theme multiple testing, but each had a different viewpoint. The first one had the dependence viewpoint, the second one had the adaptive designs viewpoint, and the third one was a Bayesian flavor. And also, we can see that the first and third one was more on the theoretical side, and the second one was applied motivated. So I think that it has still many challenges and many open problems are there, and it has many problems to be explored both from a theoretical interest and an applied interest.
Okay, great. You have done a lot of interesting problems and very good work, and in fact, excellent presentations. We are always grateful to you, Manitra, for organizing this session and for your contribution as a young researcher. In fact, you have done a lot of very good work and also motivate the youngsters through your contributions. And once again, we wish to thank you for organizing as well as chairing the session in a very nice way. We expect your continued deliberations in our coming conferences also. Thank you. Also, I wish to thank each one of these other speakers also. Let us
Thank
give
you, sir.
a clap to the.
It has been a pleasure for us to be a
Yeah,
part of this conference.
definitely. It's our
Thank you for inviting. Easy purpose.
So you can I hope your further findings in this area we hope to have in our December conference as well. Shall
Yes,
I
sir.
expect?
Yes, sir. Yes, sir. Sure, sir.
definitely.
Okay.
Definitely, sir.
Thank you.
Thank you, sir. Thank you, sir.
Thank you so much. Let us conclude the session. Pallavi, please.
On behalf of the organizing committee of WSTA 2026, I extend my sincere thanks to our session chair Dr. Montita Day for graciously chairing this thematic session and guiding the proceedings with his experience and insight. I express my heartfelt gratitude to our distinguished speakers, Dr. Montita Day, Mr. Anirban Chakraborty, and Mr. Sayandan Pol, for sharing their valuable knowledge, experience, and insights through their enlightening presentations. I also extend my sincere thanks to all the participants for their presence and participation, which contributed to the success of this session. With this, we conclude the thematic session of WSTA 2026. Tomorrow, we will be having online sessions, which will begin at 9 a.m. Thank you all.
Thank you, everyone.
Okay, let us meet tomorrow.